All right, welcome to the final session. I hope you can hear me. I think it should be better now. Uh, Today we are having the final episode for this series, for this advanced series. And today, I think I don't know what the topic says. Yeah, we'll have mixed problem solving. Today we'll focus mostly on segmentaries because some part of the theory is left. We'll focus on the part of the theory which is left and then we'll walk into the problems. That's pretty much the agenda. So today we'll do problem solving on segmentaries after having done some theoretical discussion. So roughly the agenda for today goes something like this. Just let me know if you have some difficulty in hearing me. If it is fine, then well and good. So today's session shall involve merge sort trees. We'll discuss three approaches which are followed and what we get from each of those approaches. Then we will look at probably the strongest thing in this session, which is 2D segmentaries. Strongest in the sense that this is most non-trivial out of everything that we have discussed. And finally, last but not the least, we'll be looking at quite many problems. And the problems shan't be on 2D segmentaries, they'll rather be on normal segmentaries. Hi. So they'll be on normal segmentaries, lazy propagation, and let's see. And some constructive algorithms maybe, or maybe some observational aspects. So about myself, I'm currently working as a software engineer at Google. Before this, I pursued BTech in Computer Science and Engineering at IIT Bhilai. What else? I graduated a few months back, and I've gone to the ACM ICPC regionals a few times. I've been a master in code forces, and I am a 6-star rated coder at CodeChef. That's about me, Saptarshi Mukherjee. So, any questions if you have regarding any topic pertinent thing or anything outside topics, you can ask for a few minutes because I'll be waiting till 5:37. I'll be starting at 5:37. If you have any off-topic or on-topic questions, you can ask me. Till then, 5:37 p.m. Any questions till then? So in the previous classes, maybe I can brush up a bit whatever we covered. In the first two classes, we covered tries, and today I won't be going back into tries. If there is something left in terms of problems, maybe some good problems, I'll pick them up next week. Next week we'll have the final three classes of this series so far as I'm informed of, and then we can finish off binary tries and character tries. After tries, we discussed segmentaries. We took some time to discuss the basic approaches, the range query and point update problem. We discussed why the time complexities are order log n. We then came to discuss what are the various types of problems that can be solved. We started with some segmentary. We discussed about max, min, the frequency of max and those things. And we understood the requirement of associativeness or associativity in the operations for segmentaries. And then we saw certain other problems where the problem statement itself does not tell you what exactly you should store in the nodes. But if you know what you should store in the nodes, the rest of the problem is quite simple because the basic structure is almost the same. We then covered binary search in segmentaries. That was the last topic I think yesterday. And in binary search, we actually covered two different techniques. One is implicit, other is explicit. For today's topic, the prerequisites are you should know the basics of segmentaries. You should know how basic, segmentaries work and how lazy propagation works. If you don't know how exactly lazy propagation works, then you need certain assumptions to make, and that okay, it will work in order log n time. You have to assume that range update will occur in log n time. But apart from that, there is no as such difficult thing, so not no as such prerequisites. So in binary search, when we discussed how can we conduct binary search on a certain range, what we found is if we do the binary search outside the segment tree, and for every query, for every mid value, if we query the segment tree that okay, tell me the value over here, tell me the value in this range, then this will basically consume log n into log n time, log n whole square time. And we found then that if we rather follow an implicit approach, implicit binary search, which again depends on the problem, that how you'll be applying that implicit binary search, and then it turns out we can reduce it from log n whole square to log n per query. The basic structure of the question is usually always the same. We have n numbers, we have got q queries, and we have to somewhere form such a complexity equation such that q log n is supported. We have seen that order n time gets involved, n plus q log n, this kind of an expression comes if we form the segment tree in our iterative implementation manner. And if somewhere we want to not create so many nodes, if we decide that we should not create so many nodes, we found that sparse segment trees are actually a way out. We don't have to create so many nodes. We can say that okay, we'll create nodes only when they are required. Using sparse segment trees, you don't have to create at all that kind of a structure. Even the linked list kind of a structure is also not important. A better word in place of linked lists may be binary trees. You don't need to make binary trees with those nodes and next pointers and those things. In the last class we discussed how using basic iterative implementation we can cover sparse segment trees. So coordinate compression sparse segment trees, we had a brief discussion on it, and I think we discussed some very classical problems like what is the number of inversions in an array. Okay, yeah, that's pretty much about it. Cool. So now I think we can move ahead. If you have any questions, you can ask maybe, or I'll take a while. If you have any questions for the next minute, you can ask. It's just a second. Okay. So let us come back. Yeah. The first topic that we have with us is merge sort trees. Okay. The problem statement goes like this, that you have got n elements in an array and n cannot cross 10 to the power 15. I'm sorry, 10 to the power 5. N cannot cross 10 to the power 5. All the elements are given to you. They are basically AI which can reach up to 10 to the power 9, and they have okay, something like this. And now basically you have got q queries, and every query requires you something like this. maybe we can say, okay, we can have some update operations. Definitely we can definitely have some update operations, but for a moment, maybe let's forget the update operations. Let's consider only the query part, which is given a value k, find the minimal value in LR which is greater than equal to k. So I'll give it three values, L, R and K, and the question shall be that in this range of L to R, what is the first value that you get which is greater than equal to K? So you can have many numbers, suppose 3, 7, 8, 2, 5, 4, 8, 3, and now I tell you, okay, this is your L, this is your R, and now I tell you that 6 is my K. So your answer shall be 7, because in this part this is the minimal element which is greater than equal to 6. If instead of 6 the value would have been something like 4, you would have said, okay, in this range this is the best element which is greater than equal to 4. What is my CC rating? It has been a long time since I've done. Maybe 2210 or something like that. I've been a 6-star, and it's Saptarshi 2017. You can find it out. Really? Well, I didn't feel I was doing a good job, but anyway, thank you. So, okay. Now we want to find the minimal value which may occur once, which may occur multiple times. We want the minimal value in a certain range which is greater than equal to k. Okay, I don't know. How can we proceed? What do we have to store? Suppose there is some update operation. And update operation, basically we have to change maybe one element, so I'm not worrying about its time complexity, that what will be the time complexity of the update. Let's imagine that that update will happen according to our usual means. Okay, so coming back, what is going to be the procedure to find the minimal value, or in other words, if we make up our mind we are going to form a segment tree, what should be stored in the nodes of the segment tree? Suppose I basically ask you that I want from 1 to n. Then according to the usual concept of segment tree, what we usually know is, if it is one indexed, consider that it is one index, the root should give me the answer. The root should give me the answer. The root should not ask the children for the answer, because it covers this range. If I ask 1 to n by 2, then this node should give the answer. Right? And we know one thing, that any range, if we keep the natural segmentary ranges in our consideration, any range can be constructed using order log n different segmentary nodes. Order log n different segmentary nodes actually can contribute to our entire range. We don't need to see more than that. We don't need to see more than maybe 4 log n, you can see. What is the total number of nodes visited? That is also a different question, but that is also order log n. But basically my question is something like this, that if I am questioning from 1 to n by 2, I expect this node to give me the answer, that 1 to n by 2, this is the answer. So what should this node store so that it can give me the answer pretty fast? What should this node store so that it can give me the answer pretty fast? Pretty fast means basically it should store something so that if I ask him greater than equal to 5, what should be the value? Greater than equal to 10, what should be the value? Greater than equal to 1, what should be the value? It should have the answer for all of those questions. So what is something that it should store so that it can actually answer my queries? So in case the question is not clear, the question is something like this, that for a maximum, for a max segment tree, we stored only the max. We stored that in this subtree, only the max needs to be stored over here. But if we need this kind of an API, where basically we have to find the minimal value which is greater than equal to k, it means that if there are some values, I can ask I can ask with a value of k which can make any value important. I don't know where this target value is going to fall, which means if this node does not depend on the children, it should have the property to remember all the values which are required for the different kinds of queries. Whatever query I ask, it should have that value to respond to my query. Does it make sense? So that it does not have to reach out to the children. That okay, tell me what do you have and what do you have and so on. Make sense? Which essentially means it basically needs to contain all the values. So given that, and given that you have to store all the values over which if you have any doubt you can ask, given that a node has to contain all the values that are stored within it because you don't know the value of k beforehand, how should you store the values so that the required value, that is a minimal value, can be fetched very easily? So what is the first thing that I mentioned? The first thing that I mentioned is all the values in a subtree or in a certain range in L2R, maybe in L2R of a node, should be stored in a node, should be stored inside a node. Why inside a node? So that it does not have to travel inwards to other nodes to find out those values. Inside a node. And next, what is the next point? Next point basically is that they should be stored in a manner so that the query becomes easier to respond to. So the storage should be such that the query can be responded fast. So now maybe you all can answer the question, how should the storage be? We know that all the values need to be stored. We can't do anything different, but we know that we can store it in different structures. Now, how should the values be stored so that the query can be responded fast? Forget about data structure, but what should be the way of storing? Should we store some kind of frequency array? Should we store some kind of maybe in some sorted order? Or should we keep in the unsorted order? What do you think? So you can understand that whenever I'm asking that which value is greater than or equal to k, you can easily understand from your knowledge of lower bound, upper bound and those things that it is basically a query of binary search. And when it is a query of binary search, the prime requisite is that this node should know whatever it is containing. It should know all the values that it is containing. If you have attended my previous class, the binary search that we discussed over there was slightly different because we were focusing on the leftmost index. But now our focus is on the entire range, whichever is the smallest value. So our searching needs to be done on the entire range. We cannot traverse to the left nodes. If we get something we are done, we can't do that. This is where this question is different from that question. But one thing is for sure, that if we have to do binary search for this standard application, that for a given k find out the least value greater than or equal to k, then definitely the what is that called? Where were I? Now I forgot. Yeah, all the values should be there. They should be stored in the sorted order so that you can jump into the relevant part by dividing your search space into half every time, and you can get the particular value. Makes sense? Any part which you found just it happened, I didn't get how it happened? Okay, so let us explore the different data structures. First of all, we get a data structure which is our sorted array. In our sorted array, basically if we store, and remember one thing, this is not a very easy question altogether. If I tell you there are no updates, I tell you something that there are no updates, but basically this question you have to answer that in every LR, suddenly I'll ask you that in LR find something greater than or equal to k. K can also be anything. So definitely you cannot just use an array and do something. Why? Because every time when the query comes, you have to take all the array elements, either you have to iterate through them, or you need some sorted version of that which you don't know whether it will be available or not, and then you have to pick up whichever element is relevant to you. So if you have to need a sorted version, that means plain simple array is not going to help you because all ranges are not supported. Hence, the first thing that we utilize from Segmentary is that it actually ensures that if I want any contiguous range, I can create it using at most log n nodes. At most log n nodes of the Segmentary can help me create any range of contiguous elements. We are discussing merge sort trees, Priyank. And now we are actually at the sorted array version of it. So if we keep a sorted array, what can we say? Sorted array basically means something like this. Suppose I have got four elements. Four elements in my array. So what will I say? This is basically 3, 1. Yeah, it has just started. 3, 1, 8, 2. So what can I say over here? I will basically store this as my sorted array. 3, this is 1, this is 8, and this is 2. Then I'll be clubbing these two and I'll be saying that okay, inside this you basically have 1, 3. This is my sorted array inside this subtree. Okay. And inside this subtree, in a similar manner, we will have 2, 8. So just for those of you who have joined recently, this is the question I want to answer. I'm sorry for this clumsiness. Basically, every query says that from some L to some R, tell me which is the minimum value which is greater than equal to some given K. So from some L to some R, greater than equal to some K, what is the minimum value that you can get me? Or that can have a frequency of greater than 1 also. Frequency should be at least 1. So now coming to this thing, what we actually inferred is that every node should store all the elements, so that when I say okay, you are responsible for giving me the smallest you can from your part, then I'll collect from some other guy, then I'll maybe collect from this guy. So this guy should tell me that okay, this is my value. Okay, this guy should tell me that this is my element. This is the smallest I can give you. That guy should give me the smallest element that can give us, and we'll combine them. It has to have some associative property. We know that minimum is associative. If this guy tells me that this is minimum from my side, that guy tells me this is minimum from my side, I need the absolute minimum, I can take the minimum. I know this is associative. We are very strongly utilizing this associativity. Okay. Now coming to the point, what should we store here? We will basically store 1, 2, 3, 8. That's it. This is what we are storing. If you have any doubts, please ask. What we are storing is sorted arrays. And why we are storing it? One reason is that we know that no updates are taking place. If updates would have taken place, we'll discuss what would have been the problem. But if no updates are taking place, we can create this. Now if I say that okay, I want to search from index 0 to index 2, from 0 index to 2 index, I want to search something which is greater than equal to 2 maybe. What will it say? It will say that okay, for this I need to depend on, it will come from over here, it will depend on this, and then it will come over here and this will depend on this one. Right? It will depend on this one. These two are the nodes that should return. So what will this node say? That okay, greater than equal to 2, I can return 8. So it returns 8. What this guy tells is I don't need to go to my children. I can return easily the value of 2. And when you combine them, you will get basically 2 and 8. Together you will get 2 as a minimum value. Similarly, there can be like other examples. You can search something from 1 to 3. 1 to 3 basically means that it will come all the way up to here and it will come up to here. From here it will return, suppose we want greater than equal to 4. So from here it will return 8. From here it will return that I have nothing. Maybe it can return infinity. To depict that, we can take the minimum and we can say that okay, 8 persists. Make sense? 8 is the, so if a node range is completely inside query range, we won't go down. Exactly. So the same way we discussed for range queries, lazy propagation, whenever a node is fully covered or uncovered, then we should not send to the children and bother them. We should complete it right over here. Either send the value or send that I can't give you anything. Either way. If it is partially covered, then we need to depend on the children. We will directly put down the control to the children that you all decide what to do, and they'll make the decision. Even uncovered nodes, if you call them, it won't affect the complexity. We have seen that. So till now, is what are we doing? Is that basically clear? We are basically storing the sorted versions. Yeah, for partial we go to the children. That's what I exactly mentioned. So now the thing is, how much time will be taken? How much time will be taken for this operation? We know that whenever we have a sorted array, what we are doing is basically binary search. We have to do binary search on a sorted array, on every sorted array. So if these are the nodes, maybe one over here, one over here, some basically log n number of nodes we know that we'll be covering. Log n number of nodes can help cover the initial part, the target range. So what do we know? That they are basically log n nodes where I have to do something, and in every node I have to deal with an array where I have to do binary search, and the length of whose can be at most 10. So the length of the array can be at most 10. It can definitely be smaller than that. But this is a very easy approximation. We can say that okay, this is going to be a maximum of log n. So this is basically exactly. So log n whole square, you can say. Log n whole square is the time complexity for one query. Got it? Cool. What is the size of this tree? What is the size of the segment tree? When I say size, I mean what is the number of integers that it stores. Every integer which is 32-bit in size, I am considering that as 1 unit. So I want to know what is the number of things that you have to store. Clearly the number of integers is greater than equal to the number of nodes. So only tell me the number of integers. Then I can say the total number of things is less than or equal to twice the number of integers. I am only interested in the big O notation in the long run. So I just want to know what is, okay, n log n. Let us see. So let us check over here. Basically, over here what do we have? At the lowest level, every level stores n elements. Exactly. Every level stores n elements. When you did your merge sort, then only this analysis should have been clear. That in whenever you do merge sort, there also the same idea holds. And even in segmentary, at any level, whenever suppose you are at the ith level, how many nodes is it containing? It basically contains n by 2 to the power I. Okay, n by 2 to the power I. Correct me if I am wrong at any point of time. So n by 2 to the power I is a number of right. So when I say n by 2 to the power I, what I mean is that here I equals to 0 at this level. That is why it is n over here. This is n by 2 to the power I. How many nodes are over here? We know there are 2 to the power I nodes. Why? Because here we know there are 2 to the power 0 nodes, and gradually it goes on getting multiplied by 2 every step. Then what we say is that okay, what is the total number of values then? N by 2 to the power I. This is the number of values within one cell multiplied by 2 to the power I. What do we get? N. So n is the number of integers you are going to store at every level. What is the total number of levels? The total number of levels is log n. What that basically means is that this will be exactly n log n in size. This is not the case for your standard segmentary. Your standard segmentary takes only how much? It takes basically, I don't know if the chat is active. Maybe I saw some error creeping up. Yeah, now I think it's fine. Yeah. So in our basic segmentaries, we basically have how many things? We have in total 4n elements maximum. 4n nodes basically. That forms the upper bound. And over here we can see that in order n log n, we can say that the upper bound is found. So that's well and good. It takes n log n space, which, like, you can understand whatever way you store these elements, whether in terms of sorted array or in some other manner, you need this space. And the time taken is log n whole square, log square n, we can say, per query. So in total it is q into log square n. Well, good enough. What is the drawback of this approach? The drawback is that we cannot update. Why we cannot update, or basically why updating is not easy over here? Suppose you want to update a certain value. This is basically how the segmentary goes, and this value you want to update, you have 2 over here, you want to change that to 200. What that basically means is that here the sorted array, okay, it's just one change. Here it stores two values. It stores two values, so basically they may get shifted. You may have to shift them this way or that way. How many operations? Maximum two operations. Here if you have to shift them, since 2 became 200, so now you have to again make it sorted after changing 2 to 200. So how many operations? Again n operations, total number of elements 4, and gradually it climbs over here. You get n plus n by 2 plus something, which is at least, I think it's exactly order n. So order n is the time for every update, which definitely we cannot bear, right? So order n per update gets involved. If we do update, what is the kind of update? Point update. I just want to say that, okay, a of pos is going to be equal to val. Any doubts or anything that you want to ask at this point? Because update in sorted array is difficult. Update in sorted array, yeah, not only difficult, like, okay, maybe you wrote this before and I'm reading this now. Suppose you have something like this, 2, 4, how much time is required? Basically, for every update, how much time is required? Any idea? Suppose it has m elements. How much time is required? One way is you change the element and then you do something like m log m, that is again sorted. Another thing you can do is, suppose you have something like this 9, 10. Now you're changing this to 200. So what you need to do is you need to keep on swapping with the next elements, right? You need to keep on swapping with the next element. So if you do that, it can again get sorted. It's like insertion sort. Insertion sort just works in the opposite way. It can either come back, like in insertion sort you always bring it backward, but over here you actually are sort of bringing it forward in using the same idea as insertion sort. Okay, so this is order m, linear. So okay, so we can actually bring it down to order n. Because why? Because of the GP that gets found. Over here this is n steps, over here this is n by 2 steps, and so on. N plus n by 2 plus n by 4. Y'all can help me with the mathematics. It goes up to 1, so I think it is n into how much? If you carry this up to infinity, then a by 1 minus r 2n. This is just an upper bound. Basically, you won't have the equality. I've just raised it to infinity. One iteration of bubble sort. Yeah, you can say bubble sort, but bubble sort is wrong in only one thing. Suppose you move 200, you keep on moving 200, then you see that 200 cannot be moved. What will bubble sort do? Bubble sort will then start from over here. It will take some other element. Suppose you have 400 over here, then it will take this element and move something like this. But you're not interested in that. You know that it is already sorted. So insertion sort actually uses that property that this part is sorted. Basically, in insertion sort, what it does is it takes one element, it pushes it into that sorted part. So you know that that part is sorted. Bubble sort does not know that the different parts are sorted, and definitely the parts are not sorted. There is a small difference, but anyway, the basic idea is okay. 2n order n, right? 2n order n, this is order n. So we can say that this is not good for update because q queries are there, 10 to the power 5 queries, and 10 to the power 5 being the value of n will definitely not make it feasible. So we first need to find where to sort exactly. You can find it again in order m time. Again in m time you can just move around and you can find it, and then you can go on shifting from there. That is also easy, right? Now why should it take log n? It won't take log n. Or if you use binary search, if you use binary search, it is log m plus m. If you don't use binary search, if you use linear search, then this is m plus m. In other ways, it is the same. It is 2m. So in that case, you'll just multiply this by 2, which will be 4n. 4n. That is also order n. Make sense? You cannot like you are not getting anything out of binary search when you are updating. In updating, the bottleneck is definitely the shifting part. Yeah. So moving ahead, I think we have spent sufficient time. Now the second approach we can cover very quickly. The second approach can be definitely the tree map or your C++ map. I should have mentioned it is Java tree map or C++ map, basically the ordered map. In Python also you have equivalent structures. What we can say is now the update is pretty easier. Can we store in BST instead of exactly BBST? Balanced binary search tree is exactly what these things use. So we can, in every node we can store it in a kind of map, and then whenever we have to update something, what is update operation in a map? Log m. If there are m elements, log m, because it is a kind of binary tree. So now every update operation is log m. Update is actually how much? Log n plus log n, you should say. Why log n? This log n is actually for reaching the correct node that you want to change. And why this log n? When you have reached the correct node, if its size is m, then you have to do that update operation. I'm sorry, just a second. I'm sorry. So this is multiplied by this. Yeah. So basically in all the nodes which are basically lying from the beginning to this, from the root to that leaf, you have to basically run that what to say, tree map update operation in every node. So if you run in every node, how many nodes are going to get involved? Log n number of nodes. And in every node, how much time is going to be taken? It depends on the value of m. So this is the upper bound, it is log n. You actually have it from log 1 to log n. Now you can do some mathematics to find out a better value, but you can take this like it goes up to here. Makes sense? Any questions? Yeah, so I think it is pretty much, the mathematics is easy. In the topmost value, this is the time which is taken. In the next one, this is the time which is taken, log n by 2. In the next one, this is the time taken, log n by 4, and so on, log 1. And now when we add them up, what do we get? Log n plus log n minus 1 plus log n minus 2 plus dot dot dot. This is 0. And then we can say this is nothing but log n whole log n into how much? Multiplied by how many terms are there? We know that is again log n minus what is these many terms? Maybe 1, 2, and it goes up to log n. So log n into how much? Log n minus 1 by 2. So it doesn't make a difference. You can see that it is something like n square minus, and you can do some calculation. What will you get? This term gets okay. So you're getting something ordered log n. Okay. Just look at this minus 1 plus 1 if that makes a difference, else this is what we are getting, right? I suppose we will use tree set in each node. Exactly. I'm sorry. So map, basically I meant what kind of a data structure. So yes, we don't need a map. We basically need a set. We need a set, and it is exactly the same thing. The way, basically, the thing that we have mentioned, that is the same for both. For update, we need to unrelated, but in C++, tree map is just map, and hash map is ordered, unordered map. Yeah. For update, we need to remove, then insert. So 2 into log n. Yeah, 2 part you can just ignore. I suppose that. So are you convinced that we are getting it in order log n time? So log n whole square was just an upper bound. You can actually form it in log n time. Make sense? And did this analysis look good? How I did this? 1 plus 2, basically how many terms are there, that is how I formed this. So if I have not made any calculation mistake, this should be the final answer. But anyway, what we still have not improved probably is the querying part. Let us see what the query part is going to take us. Query part means we have to ask how many nodes? We have to basically ask log n nodes. We have to basically ask log n nodes, and here we don't have that kind of a guarantee that we should take this node, not take that node, or we basically have that kind of a recurrence. We know in each of them the upper bound is that we can have log n as the time complexity for fetching that element. target element. So our query operation, and then we have to do some minimum operation, which is relatively easier. So again, log square n time, according to a trivial analysis, is going to happen, because we are going to use those tree structures in log n different nodes. Every node has at most n elements. Now again, you can try like creating situations, and you can try to see whether it can be optimized or not. But according to this analysis, maybe you can get a hope that okay, even this can come down from here. But I'll leave that to you. You can find it out if you are interested. But if everything is clear up to here, what we basically want to improve this to is to make the query part log n. We want to make the query part log n. That is what we are interested in. So we want to use a merge sort, or we want to form a merge sort tree. This is whatever I've discussed till now. This is exactly a merge sort tree. In merge sort, exactly whatever you do, you are doing exactly the same thing over here. So for forming a merge sort tree which can support better queries, we use a technique called fractional cascading. Fractional cascading. I won't go too much into the depth of this particular topic, because fractional cascading has got much stronger applications in other problems. In merge sort tree, we have lesser requirement. We don't have too much requirement. So let us see. Basically, what we'll say over here is that don't do binary search in log n different nodes. Over there, what we were doing is doing binary search in log n different nodes. Here, what we'll say is don't do binary search in log n different nodes. Do binary search in only one node, and utilize that binary search to find out all the target elements in all the different nodes. So this is how it goes. This is my array in my top node, my root node, where I have it sorted 2, 3, 5, 6, 8, 9, 10, maybe something like this. I have some elements in the left, some elements to the right, and they are also kept in the sorted manner. So maybe I have 2, 6, 9, 10, and maybe I have 3, 5, 8. Realistic? 4 elements to the left, 3 elements to the right. And then I can say that okay, they are now in two partitions over here. We have 6 and 10, we have 2 and 9. And then we can say over here also we have the difference. We have 3 and we have 5, 8. And over here also we can definitely create the partition in any manner. Suppose these are the partitions, 9, 2, 9, 2. And then over here what we can say is 5, 8. So this is how they are connected. Now basically what we do is, this is our basic sorted array, what we keep. For a moment, forget about updates. Again, for a moment, just forget about updates. We just want to improve the query part. One thing that we can do easily is, for each element over here, I will keep a pointer to my children, that which are the elements in those nodes, that are just greater than equal to me. So suppose for 5, I will say point over here which is the element just greater than equal to 5. So it will tell okay, it is 6. And then I say okay, point me over here. It will tell okay, it's 5. What will it store? It will basically store the index. Along with this, it will store another array which will contain the indices of which is the best left element, or best element in the left child, which is the best element in the right child. There are many things I actually discussed, so if you have any problems, just feel totally free to ask any question, because I've spent more time in it, so it makes sense to understand it in a good manner. Now what I can say is that okay, I need, for this 5, I need the next greater elements over all of these things. So when I come over here, I can check right from 6. Why? Because I know that lesser than 6 there is no value which is greater than equal to 5. So we will skip those internal binary searches. Exactly. We don't have to do binary search, we'll just keep these pointers. It is very easy. Whenever you combine this, suppose you are combining this, you are combining this array, you're combining this array and you're combining this array. At this step only you can basically do this step. You know you're getting 2 over here. Okay, and then you are taking 3 over here. From there you understand that okay, this 2 is going to point to this one. And then when you are taking 3, what you basically have to do is that whatever previous elements have not pointed to any element of this array, you need to point that over here. Next time you'll say okay, I'll take 5. This one definitely will get pointed. It will not point over here to anything. Then you will say I will take 5. So what will 5 do? 5 will just point to it. Then you take 6. What 6 will do is 6 will basically point to it, and then whatever are remaining, these two things have not pointed to anything in the left array, they will all point to 6. Okay, it works in this manner. It can be an easy kind of a looping thing, and in amortized manner you can actually verify that it will run in exactly order m time. You have this in order m time, this one also will take order m time to form these pointers. For every update we will also need to update the auxiliary array storing the indices. Isn't it slower? Yes. So consider that there are no updates for the time being. Consider that there are no updates for the time being. Okay, so if there are updates, you can think in terms of like amalgamating this approach with the other approach that with the use of tree map or tree set, but for the time being, just throw away that update thing. We just want to improve the query part because that's quite great. You can show the pointer logic with an example. Yeah, okay. Yeah, so maybe these are the pointers. Suppose for 5, let us see what are the pointers. We have this as the pointer, we have this as the pointer. Then for 6, we will have what pointers? 6 will point to 6 and 6 will point to 9. 6 will point to 9 over here. 5 will point to 5 and 5 will point to nothing. 5 will point to basically the index after this where there is nothing. Okay, something like this. Then you can say 6 will point to this, 6 will point to this. 2 will point to, or 9 will point to 9 and 9 will point to something that is ahead of it. Then you have 5 will point to this, 5 will point to this, and you don't have anything over it. It will not point to anything. So when I now say that my k value is 5 and my LR is something maybe where 5 is not present, so maybe I am querying about this part. Maybe I am querying about this part. Okay, from okay, I've partitioned it. Yeah, I am querying about this part. For the first 5 elements, maybe I want to find which is the element greater than or equal to 5. So what will it say? That this is my node that I need to check, and then one node basically it will come up to here. So it will get the 5 over here. From here it has to send back what? It has to send back 6. How can it find out? It can basically do something like this. It comes over here, it knows that okay, 6 is the target element. It comes over here and it knows that okay, 5 is the target element. I have found 5. Now suppose the case was slightly different. We want only in this particular range. In this particular range, you can say. Now this is the sorted version of it. We want in this particular range basically 2 to 3. This is my array index range. So we can go in this manner. We can basically run up to here, and which will be my element? I can say that okay, I found out 5 by a binary search. Now I'll go down, I'll come over here, and 9 is my answer. Okay, can you see that we are not doing binary search? We are just traversing down the merge sort tree, and we are making use of these pointers which are pre-computed. These pointers are pre-computed. So does it make sense that as you go down, you know how to go down? So what is the number of pointers? Again, that is easy. So if you want the discussion for how to code it, then you can just focus on the combine part. In the combine part, you can do something like this. There are many approaches actually. In the combine part, what you can do is, this is your combine function, and what you do is you will run a for loop for I equals to 0, I less than maybe n plus m, I plus plus, and what you will say is you will have some j and some k. Okay, and then you will say that if a of j is less than b of k, then basically what you do is you say that your merge array, suppose that is c. Okay, then you say that c of okay, so you do something different. You basically have k value starting from somewhere else, but let us take this convention. You have c of I equals to a of j, and then you do something like j plus plus. This is what you do. So before j plus plus, do one thing: keep two vectors. These both of these will be vectors, left in I and left in j. I'm sorry, left in maybe 1 and left in 2. Okay, whatever are remaining in these two vectors. Now what you will say is that okay, aj is less than bk, so left one dot push pb, you can say a, I'm sorry, whatever you have, j, right, j. By this what I mean is that next time when b is going to win, when b is going to be entered, that b is going to tell, yeah, I need to be pointed to by these elements. I need to be pointed to by these elements. What I basically want to say is that this aj, when you bring this aj doesn't know which ones to point in b. It doesn't know which ones to point in b. When you get the next bk maybe, you will say that okay, now all these things, all these a's which you have added over here, they should all point to this particular bk. Okay, they have to point to this particular bk. So that is what I'm storing over here. Now you can do something like this, that run a loop maybe while something, and which will basically iterate in left 2. In left 2 you will say something like this, that another pointer, that whichever we will keep, we will say that ptr2 of j, I'm sorry, ptr2 of whatever pointer we get from here, or maybe I don't know what example, idx, ptr2 of idx equals to j. Yeah, what I'm basically telling is something like this: when some aj comes over here, what it will tell is that before this, whatever b's have come, now those need to point to it. Basically, those need to point to it, aj. They all need to point to aj. That is why I marked here j. I say that they all need to point at j. This thing need to point at j, these things need to point at j, and some plus plus thing definitely will be occurring. Okay, after this, idx plus plus you can say. So I just wanted to give the rough idea. The combine operation will not be that difficult. You can just sit on it. I think on editor it will be far more easier. But okay, so what are we doing over here? This is basically the concept of fractional cascading, that if you have to find out from many different lists that what is the position for this element in this list, what is the position in that list, if you have to find out all those things, you can basically do some pre-processing of pointers, and then later on you can do in only one list. There will be only one list where you can do the binary search. You will get one element. From there you can travel to all the parts and you will find the exact elements. So one binary search will do the task of so many binary searches, that you can actually optimize, and hence what is the operation of every query? It is login. So the operation basically is login per query, and what time is taken to form this? We know that the total build time over here is n log n, and we also know that together with this n log n, there is also an extra 3. Like we already know that there is some n log n already there in any merge sort tree. Any merge sort tree will be of some kind of n log n. We have even 3 times of that. So it is a bit expensive in terms of space. But in terms of implementation of query, it is very, very promising. So per query, it is definitely order log n per query. Is it clear? So it has been quite a long part. So there has been some time since I've last taught segmentaries. I taught maybe 2 months or 3 months back, and hence I don't remember how much time it took the previous time. The idea, yes. The implementation, no. Is it? So anyway, you can just try it yourself. Again, a rare occasion you will get this kind of a question. After this, but maybe towards the end, the implementation, no, but I'll try out myself. Okay, sure. Fine. I think if you're convinced with this, we will move to 2D segmentaries, which will be a bit hard. So we will take it towards the end. We will actually do it towards the end, maybe taking at a stretch half an hour or 45 minutes. But now we'll move on to some other topic. Okay, we'll move on to a fresh, maybe a fresh problem. And the problem is actually nested segments. Nested segments problem. So basically, you have some elements. How many numbers are there? Basically, you have 2n integers. Every integer, ai basically belongs to 1 to n, okay, and every integer from 1 to n occurs exactly once. Every integer occurs exactly twice. I'm sorry, exactly twice. So let me take an example. Suppose that n is equal to 3. So we know that 2n means 6. 6 values are going to be there. Suppose 1 to definitely we have 1 2 3. So it can be something like this: 2 3 1 3 2 1, something like this. Okay, so this is one instance of the problem. And now what we have to find is that let's visualize it like a segment. So a segment is one which starts and ends with the same digit. So this is one segment. This is the segment for the digit 1. That is a segment for the digit 3. And this is a segment for the digit 2. So now, how many segments are nested within 2? Within a certain range, how many segments are nested? It is basically the number of segments that start and end within that range. Okay, if these are happening, if these 3 are different segments inside a certain range, we will say 3 is the answer. So we need to answer for all these indices, for all these values of ai, for the value of 1, for the value of 2, for the value of 3, how many segments are nested. So within 1, we know that they are not nested. Within 2, we know that okay, 1 is nested, so basically we have 1. Within 3, we know that none is nested, so it is 0. Okay, so in this example we have 0. We can have many other examples. If you have something like this: 4 4 3 3 2 2 1 1, then what will we say? For 4, how many segments are nested? 1 2 3. 3 are nested. For 3, how many are nested? We have 2 and 1, so 2 are nested. For 1, how many are nested? 0 are nested. For okay, I'm sorry. For 3, 0 are nested. For 3, 0 are nested. For 1, 0 are nested. For 2, 1 is nested. Make sense? The question is pretty much understandable. For every value from 1 to n, we have to say that for this particular segment, how many segments are inside this segment? How many other segments are located strictly inside this segment? They start and end within this segment. This is the problem we have to solve, and yeah, n goes to 10 to the power 5. So you have 2 into 10 to the power 5 values in as the input. So the order in which the input is given is definitely important for us. That is the order in which 1, 2, 3, 4 all these values are placed, and that is the order on the basis of which we have to find out what are nested within what. So maybe you can come up with your approaches. We have some time. We can definitely make it fast anytime. So is there anyone who feels that, okay, had that combine function been discussed in a bit of detail or precision, then it would have been better? That is not related to segment trees, that is something related to merge sort. So it would be a good exercise if you try for yourself. I'm gonna need to rewind and watch at 2x speed. I was okay. So the question in words is, for every segment, which is nothing but I to I, any I to I, you have to say state how many segments, how many other segments are located completely inside it. For every segment you have to mention this. Any suggestions, any approaches, anything? It would be nice to keep it interactive. I can't see your chats if you haven't subscribed, I think. So maybe you can subscribe and then write down. Then we can see your answers, and that can help all of us, I believe. So see, whenever you're solving questions on segment trees, there is only one requirement. You need to understand what you're going to store everywhere, and then the rest of the things are pretty easy. You just have to figure out the statements for the update and query. But the important thing is what you need to store everywhere and when do you need to store it. So in this question, many things actually become important. You need to decide when should you store which part. And this question is definitely one of the very unique types or one of the very important types of segmentary problems. So any person who takes a class on segmentaries, you will find that there are some categories of problems that it discusses. This is one of those good categories. Okay, so maybe we can start. Maybe because it's a large algorithm. I'm sorry, not a large algorithm, but anyway. So where are we? Okay. So when we are coming to a certain value, what do we need? When we are coming to a certain value, we need to first of all know that is it the first occurrence or the second occurrence. If it is the first occurrence, then I can say that okay, till now I have not yet seen the second occurrence. So what my strategy is something like this, that you will go rightwards from here. You will read the elements towards the right. And whenever you sit on an element, if you know that this is the second occurrence, then the idea is that go to its first occurrence, sit on the range between the first occurrence and the second occurrence, and find out what are the elements that have started in it. What are the elements that are started and ended in it? Both started and ended in it. This is a complex thing. What I'm asking is something like this, that when you come to 2, you need to know that, okay, now between my first occurrence and my second occurrence, what is the number of segments that have started and ended? You know already that, okay, this is my first occurrence. How? Using a simple hash map or any simple structure, you can understand what is the first occurrence. So you get the values of L and R very easily. You can get L is equal to 0, R is equal to 4. Now if you say that, okay, in 0 to 4, in this range, I want to find out, or maybe in 1 to 3, I want to find out how many segments have started and ended. Maybe you can say, okay, 1 to 3. I want to find out. Why 1 to 3? Because I'm omitting this particular 2. From 1 to 3, I want to find out how many segments have both started and ended. Now see, this is a bit tricky. Why? Because we can store the starting points in segmentary, we can store the ending points in segmentary. If we store both of them, then the question is that how can we understand which are the points which are having both starting and ending points in the segmentary? Okay, suppose this is a segmentary, and or this is suppose the range 1 to n, 1 to n. I said that, okay, or maybe 1 to n. So I will say, okay, in this particular range, or maybe 1 to 2n. Yeah. So I'm searching for this particular range. I've caught up. Can we pre-compute all the segmentary indices and sort them according to first value? Okay, fair enough. If there is any valid pair, then the inner segment will always go after the outer one. Sort them according to first value. Okay, fair enough. Fair enough. So what Shubham says is that we will be sorting on the basis of first value. So every pair is something like this. We have something like AI, BI. Then we'll sort on the basis of first value. So we have, and in case of equal, by their right border in decreasing order. Okay. So what example should I take? Maybe okay, that particular example which we took, 433 21124, 433 21124. So now what we know is this is 0 1 2 3 4 5 6 7. These are the indices. So okay, on the basis of first, in case of equal, we know that the first value won't ever be equal. The first value won't ever be equal. So we can write 0 7, then we can write 1 2, then we can write 3 6, then we can write 4 5. Right? Right. Now what should we do? So suppose for 0 I want to find out, what shall I do? Or do you have some other way of finding out? X, and then we will say that, okay, maybe whatever elements we have seen till now, we need whatever pairs we have seen till now, we need all those pairs which have started after 1. Definitely, like I don't know, like which again we again need like this range. How do we, given these pairs, how do we actually impress upon them this particular range that we need from 1 to 2? How about as we iterate? But please think in simple terms and try to involve the segmentary, because segmentary makes our task easier. Try to understand how segmentary makes our task easier. So try doing simple things that, okay, we are just iterating. Forget about sorting for a moment, because for sorting again you have to, anyway, you can take sorting, that's not a harm. But try to think simple maybe. How about as we iterate, we can keep the maximum right border stored. And if the next segment falls under it, then we increment. If the next segment falls under it, if the next segment falls under it, what is guaranteed? Suppose I've read something, I've covered something which is having 7. I expect that you are asking me to iterate in this order. So okay, we'll iterate in this order, and then I found 7 as the highest. Next time I find something like 6 and this is 4, 6. That is good. That is good. Definitely. Definitely we will add this within this. Exactly. We know that this value is occurring after this value. Whatever occurs over here is lesser than this. So yeah, the thought process is absolutely correct. This will be greater than this value and this value will be lesser than this value, which means that okay, if this it is less than the minimum, then we can add it over there. But again, the question remains that maybe it is not only 7, maybe there can be some other values. Suppose this was 8 and there was 7 elsewhere. 7 is not the maximum. You should have added this under 7 also, right? So when you are reaching a 4, 6, this kind of a tuple, you should add it wherever applicable. It is not important or necessary to use segmentaries. If you can come up with a solution without segmentaries, it's very good. But maybe like let's proceed in this manner. That for this one, I need to check which are the elements it comes under. If I only need the number, that is a very different thing. If I only need the number, then I can just do a simple thing that okay, find out by binary search or by some maybe some policy based data structure can directly help. I want to find out that how many elements are greater than 6. Okay, how many elements are greater than 6? We can directly search for it, and then later on we have to just add this to that data structure. We have to add 6. So now that could have yielded us the total number, but we need, for every segment we need this number. We just don't need the total number. For every segment separately we need the number, right? So I need to explicitly say that okay, this needs to be added to all these numbers, and adding to all the numbers means some kind of a range update. Range update means again coming back to the kind of things that we do in segmentaries, right? So yeah, the approach is good, and from here also you can see that okay, you have actually done it, right? Using segmentaries, this is almost done, right? What you can see is that when you read something, just compute for itself and store this highest value. Store this highest value somewhere in the segmentary. That okay, here I have seen something. Some segment has ended over here. Next time when you come to 6, what will you say? From 7 to infinity or from 7 to n, find out how many numbers have been seen till now. Find out how many numbers have been seen till now. Just a second. Yeah. So I will lie in all those numbers. So you have to do a range update kind of a thing. That okay, add me to all those numbers wherever you see something. But just a second, there is a problem. No. You have to add for this value. Basically, you have to add to all the elements which are greater than 6. So it is not exactly the same thing. Maybe you have to think just a bit different. Can you see where the problem comes? In a segment tree, I want to add to only those nodes. You have something like 7, you have something like 8, you have something like 9. I only want to add to those nodes, or maybe 19. I only want to add to those nodes which have been seen over here, which have been seen till now. There are 9, 10, 11, 12 also, but they have not been seen till now. But these elements have been seen till now, previous to it. So we have to go and add to those elements and their ancestors that we have seen them, something like this. So let us maybe disregard this. You can think on top of it. Maybe you will get some answer. But let us think it in a different way. Let us try to utilize this particular order, the way we go. If you have any other approaches, if anybody has any approach, you can tell me. Meanwhile, I'll start discussion on it. So what we'll do is, when we see that this is the first occurrence, we won't care about it. We just store it. That okay, 4, this is the first occurrence. For 3 also we know this is the first occurrence. For the next 3 we know that the previous occurrence was at 1. Now what shall we say? Using the same idea that Shubham mentioned, what we'll be doing is, for anything that we'll be visiting after this, what do I know? That the last occurrence is closer than the starting occurrence, right? Last occurrence is closer than the first occurrence for any of these things. Consider for 4. 4 can occur up to here, it can occur up to any place. What can I say? That the last occurrence is closer than the previous occurrence. So, maybe I'll speak this in Hindi because it's an important thing. If any of you is uncomfortable in Hindi, then do let me know. I'll speak in English as well. हम क्या बोल रहे हैं कि जब हम 4 में जाएंगे, हमें पता है कि 3 एंड हो चुका है. अगर 3 एंड हो चुका है तो हम क्या बोलेंगे कि 3 का सेकेंड ऑकरेंस इसके पास है और 3 का फर्स्ट ऑकरेंस इससे थोड़ा दूर है. एंड व्हाट दैट मीन्स इज कि अगर मैं ये इंश्योर करूं कि 3 का फर्स्ट ऑकरेंस मेरे सेगमेंट के अंदर है, तो क्या मैं ये इंश्योर कर सकता हूं कि 3 का सेकेंड ऑकरेंस भी मेरे इस सेगमेंट के अंदर है? Feel free to tell me that you are not comfortable in Hindi. You need to be spoken to in English. I'll speak in that. So what I'm doing over here is, या मैं जो इधर कर रहा हूँ कुछ ऐसा है. मैं बोल रहा हूँ किसी भी एलिमेंट पर जब मैं हूँ, मैं देखना चाहता हूँ कि उससे पहले मेरा जो स्टार्टिंग पॉइंट था उसके बीच में इससे पहले जो भी मैं देख चुका हूँ वो सब स्टार्ट किया है कि नहीं. अगर स्टार्ट किया, मुझे क्या पता कि वो एंड भी किया है. तो मैं चाहता हूँ ये देखना कि जो जो एंड किए हैं वो इस इंटरवल में स्टार्ट किए हैं कि नहीं. राइट? सो बेसिकली अब स्ट्रेटेजी मेरा क्या है कि जो जो अभी तक एंड किए ही नहीं, मैं उनको सेगमेंट्री में स्टोर ही नहीं करूंगा. आई वोंट स्टोर द नोट्स दैट हैव नॉट एंडेड. ओनली दोज हु हैव एंडेड, उनका मैं स्टार्टिंग पॉइंट स्टोर करूंगा. स्टार्टिंग पॉइंट अगर मैं स्टोर करूंगा तो मैं किसी भी रैंडम इसके लिए कह सकता हूँ, ठीक है, मेरे इस रेंज में ढूंढो कौन कौन से नोड स्टार्ट कर रहे जो एंड कर चुके हैं. तो इस रेंज में जो स्टार्ट करे डेफिनेटली यही कहीं पर एंड कर चुके हैं. क्यों? क्योंकि उनको मैंने पहले विजिट किया था. एंड कैन वी से दैट वी आर डन? सो इन द pseudocode format, this is basically what I'm doing. Whenever, maybe for I equals to 0, I less than 2n, I plus plus, if first occurrence, I'll just write it something like this. If first occurrence, then just store it. Store a of I, because we only store the ones that have already ended, right? Already ended. So store ai equals to I. Else, what we'll say, if it is not the first occurrence, this thing we can easily store, I think, using a single counter. We can easily store it. Next, if we see that if it is not the first occurrence, what we'll say is add this in the segmentary. So update in the segmentary, something like this. Store of ai, मैं चाहता हूँ इस पार्ट में घुसाना. स्टोर ऑफ ai मतलब ये जो i है इसमें मैं चाहता हूँ कि यहाँ पे अपडेट करने के लिए. सो आई विल कॉल द रूट इंडेक्स विच इज आई थिंक 1, जो अब मेरा रूट का इंडेक्स है. आई विल सेल tltr इज समथिंग लाइक दिस 0 to n minus 1, and then I'll say that okay, add it to this position. What is the position? The position is going to be store of ai. मैंने i क्यों नहीं लिखा है? बिकॉज ये i चेंज हो गया है. मुझे अभी क्या पता है कि कुछ एक i था जहां पर मैंने 5 देखा था, तो ये i सेव हो गया था. i इक्वल्स टू 3 मान लेते हैं. नेक्स्ट टाइम मैंने i इक्वल्स टू 8 में देखा फिर से 5, तो मैंने क्या किया, ये 5 जब मैंने देखा, ये सेकंड ऑकरेंस है, मैं किस में जाऊंगा? स्टोर ऑफ ai, मतलब इस वैल्यू पे. मैं इस i पे जाऊंगा, ऐसा नहीं कि इस वैल्यू पे, इसमें नहीं. ठीक है, मैं इसको सेव करूंगा. एंड एज अ रिजल्ट व्हाट डू वी गेट? सो दिस इज स्टोर ai. इस पोजीशन पे मैं 1 ऐड करूंगा. राइट? अब मुझे क्या पता है कि इससे जस्ट पहले या इसके बाद भी हम कर सकते हैं कि just see out or printf or whatever you do, get store of, okay, I'm sorry, ये इसके अंदर होगा. तो else जब ये कंप्लीट हो रहा है तभी मैं कैलकुलेट करूंगा. सो स्टोर ऑफ ai +1, वहाँ से मैं i -1 तक देखूंगा. दिस इज माई lr. वहाँ तक मैं देखूंगा कि व्हाट इज द टोटल नंबर ऑफ एलिमेंट्स या फिर टोटल सम ऑफ एलिमेंट्स, या सम सेगमेंट्री हम लोग एज्यूम कर सकते हैं. विल बेसिकली ऐड ऑल दिस थिंग्स 1 0 to n minus 1. okay, initial things, and then it is nothing but end. Anyway, however you choose to display it. So this is the exact implementation. बाकी आपका सम सेगमेंट्री है. और कुछ नहीं. The rest is your sum segmentary. Is it clear? कोई डाउट्स है यहाँ तक, या फिर इसको भी कुछ दिखाना है कि ये क्यों काम कर रहा है? आई होप थोड़ा समझ में आया है. Like at least maybe some of you can say if you have understood. So what I basically wrote here is, if I have to make it clearer, get the root index. No, it makes sense. Okay, 2n minus 1 and store AI is nothing but the previous occurrence, the previous index, plus 1, y plus 1, because I'm checking just after that. Then I'm checking just before the current index, and that's it. If you do this get operation before this if else or before this update, if you do this, then the advantage is that you basically don't have to write this plus 1 and minus 1. Okay, you can omit this. Anyway, I think that's fine. So let's proceed to the next version, which is again similar, but try to use the same kind of trick just here and there. That problem is actually intersecting segments. Intersecting segments. And this is also self-explanatory. What we want is in every segment, we want to know that how many other segments have one point lying inside this. So within this segment, how many segments are intersecting? We know that this is one point and this is another point, so there are two segments which are intersecting. This is not intersecting, so we will say for this segment it is 2. For this segment, what is the value? Again it is 2. For this segment, okay, here for all of them it is 2 basically. Yeah. So now find out for every segment what is the number of other segments that intersect with it. Is the question clear? For every segment, print the number of other segments in fact, whose only one endpoint, this is not a very good English, but I hope it works, whose only one endpoint exists within the segment. Okay. Sample case, again, if we take something like this, these are the numbers we have 2n numbers, so we have something like this: 4 1 1 2 3 3 2 4. Over here what can we say? This for 4 basically it is 0, for 1 it is 0. Okay, for all of them it is 0. I don't know why this kind of examples are coming to me today. Let's change something over here. Maybe 2 3 2 1 3, maybe 1 4 3. There we go. So now we can say this is basically the array. Every number occurs exactly twice. So 4 intersects with only 3. So for 4 we know the answer is 3. For 3 the answer is 1. Yeah, 1 intersects, 2 intersects, and 4 intersects, right? Yeah, so it is 3. For 2 What do we know? This is 2, so only 3 intersects, I believe. So only 3 intersects, only 1. And what else? I think I've written it wrongly. For 4, only 3 intersects. So what this basically means is that only one number intersects. And for 1, basically how many numbers intersect in this range? How many are either starting or ending? It is 1. Okay. So these are the values. You can tally them and try coming up with the solution. Just try to do in the similar manner. Just try to do in the similar manner. And what is similar manner? Try to keep as much code unchanged as much possible. So look at this code, try to modify least number of lines. So when I say that, first intuition should be, let us keep this if part exactly the same. If and else. It should be within this and it should be if else. The print statement should be over here, and yeah. Rest of the things you can think of changing. Take 2-3 minutes and try to answer. If anybody wants me to repeat the question, kindly put down in the chat. Keep in mind that your chat will be visible to me only if you have subscribed the channel, so far as I know. So yeah, so we have 2n integers. We have 2n integers. N goes to around 10 to the power 5. And this is one example where n is equal to 4. Every number, the starting point and the ending point, marks they together mark a range or a segment. This is basically a segment. Okay. For this 2, basically we can say this is a segment from this 2 to this 2. For 3, this is a segment from this 3 to this 3. For 4, this is a segment. So these are the, sorry, I just stretched it a bit. These are the 4 segments. For every segment, you need to answer what is the number of other segments which are not lying completely inside, which are not lying completely outside. They are having one of the endpoints within this. Is that clear? So over here you can tally these values. For 1, that is a segment corresponding to 1, what is the number of other segments which are intersecting? We basically have 3 and we have 4. So there are basically 2 segments. Nobody pointed out. So we have 3 and we have 4. For 2, how many segments are intersecting? We have 3 and we have 4. Again, we have 2 segments which are intersecting. So for 3, how many segments are intersecting? For this 3, 2 is intersecting, 1 is intersecting, and 4 is intersecting. So it is 3. And for 4, how many segments are intersecting? Both are lying inside, only this 3 is intersecting. Okay, that is why these values. You need to tell these values. Make sense? Okay, I'm wrong. It is 1 only. Yeah, it just slipped out of my mind. So for 1, if we see how many segments, this segment is lying completely inside, this segment is intersecting, this segment is again lying like it is involving this one completely inside. So this is also wrong. Okay. So yeah, or maybe the endpoints are completely outside. So only 1 is going to be the answer. Similarly, we know that for 2, this is the segment. We know that the segment for 1 is lying completely outside, 3 is only relevant, 4 is not relevant. So yeah, over here also 1. Yeah, right. When ending point, we will keep, we'll only keep intervals if their starting point has come. We'll only keep intervals in segmentary, I hope. So you are going to pass the entry when the starting point has come, I hope. And then we will remove a starting point also from segmentary. When ending point of any segment comes, we will remove its starting point. Think about it a bit. If we remove the starting point, what this basically means is that we are going to disregard the starting point. So now the starting point won't make any sense to us, right? If we say that, okay, first we'll keep the starting point and then we will do all the range queries. Whenever the starting point comes, it will be incremented. Now if we say that we are adding the ending point and we are removing the starting point, what we are doing is that if both the starting point and ending point lies within some range, only the ending point will be counted. Only the ending point will be counted and it will be incremented. So okay, so when we are at ending point of any segment, we will query from its starting point to its current index -1. Yeah, this part is okay, but I'm only skeptical about the previous part. What I mean is that what you are saying is something like this. In this range, maybe you will say that, okay, this is my starting point for a particular segment, and then I face the ending point. When I face this ending point, I'm removing this one. Now I know this is another point, and for this was the starting point. So I'm going to check this range. So in this range, what will I see? This, for this guy, this will be a +1, and I don't know where this one was. I don't know whether it was here or it was over here. If it was over here, fine, I should be taking this. If it is over here, I should not be taking this also. Got it? So I'm not able to discriminate. If I remove this, then the story is over. It is not at all influencing the answer. So basically for I, segment J intersects if both starting and ending points if both start and end of J are greater than or both less. Yes, that is correct. What you have mentioned is something like this. This is for I, so this is I1 and this is I2. What you are mentioning is J1 is less than I1 and J2 is also less than I2. But this is also the case, right? Here also I can say that J1 is less than I1 and J2 is less than I2. Clear, Bharat? We won't keep ending point also because the segment is already over. Now see this. Now see this, Priyank. You are saying we won't keep the ending point also. Very good. Okay, where did I mark it? If you don't keep the ending point, what you are basically saying is I'll basically forget this. If I forget this, see what happens. I have nothing over here. Now if this guy tells me that my starting point is over here. This was J guy, J1, this was J2. I have said whenever I face J2, just don't keep anything. Don't keep J1, don't keep J2. For I2, what will I say? Go to I1. And between I1 and I2, you won't find anything, but you should have taken into account J2, right? Yeah, yeah. So good attempt, but now try to recover this. And Bharat, I hope you have got the idea. The inequality which you said is correct, but that is not just exhaustive, or maybe that is not very, uh, very much a singleton statement for the answer. Or does this have any correlation with some previous problem? I just joined now. Yes, according to the previous problem, that can be very easily solved if you have the pretext of the previous problem. But you can think of this as a different problem. What I basically want is in the previous problem, I did something like this. I moved from the first index to the last index, and then I was taking some decisions that if this is the first occurrence of the number, do something, else do something else. This was for a different problem. I want you to do a similar thing over here. So what should you do? When you do this, that when you face a second occurrence, I want you to print the answer. So okay, I've got the second occurrence, and this is the answer for this segment. I want you to print it right over there. That is the only thing. I'll spare one more minute for all interesting conversations of this kind, and then we'll proceed to the answer. So maybe today discussing 2D segmentaries shall be a bit of a headache. You can that will be a public opinion. If you say I'll be teaching, else I won't be teaching. If you want only the high level overview, I can give that so that you can then study it later on somewhere else and you can find some interest. Else we can completely leave it, or if you want even the codes so that that can give you a more concrete idea, we can even take that. So that will be totally on you, public opinion. Let us see this first. Take your time, and there are not only two students over here. I want even the remaining to be participative. That is only for your benefit. Yeah, exactly. We want only those points which have either started or ended, but not both. Previous problem we discussed which have both started and ended. Can we use toggling logic? What is that? What is that toggling logic? Is there anything that you have just framed? Thinking in terms of parity. Okay, think in terms of parity. don't think too complex because the problem does not require that. In fact, think very simple. What do you need to do? Just reach the point. What do you need to do? When you get to this J2, when you know that J1 was there, suppose you know that before seeing J2, you know that J1 was there. What was the reason to have J1? So that's any I1 which will come can always, or any I2 which will come can always say, okay, between I1 and I2, if there is J1, I should take that into consideration. So a sum segmentary can directly tell that in this range, how many J1s are there? I'm sorry, how many ones are there basically in those J1 positions. Next, when you get J2, what should you do? Is this important? Is this not important? Like, what do you think? What should you do? How many cases are there? When you get this J2 over here, this is important. You need to place this, you need to decide whether to place this J1 and J2 for which guys? For the guys which are lying to the right. जो राइट में लाई कर रहे हैं उनके लिए आपको डिसाइड करना है कि जो राइट में एंड होने वाले हैं उनके लिए आपको डिसाइड करना है कि इन दोनों को हम क्या स्टोर करें, स्टार्ट और एंड को, दोनों ही जरूरी है, तो स्टोर क्या करें. तो एक हिंट देता हूं, ये सोचिए कि क्या दोनों ही जरूरी है, आर बोथ इंपॉर्टेंट नाउ. इसके राइट में जो जो चीजें एंड होने वाले हैं क्या उनके लिए दोनों ही जरूरी है? वन वर्ड आंसर इज यस, इट इज इंपॉर्टेंट बिकॉज अगर एक को मैं हटा दूंगा तो एक इंफॉर्मेशन का लॉस हो रहा है. वो आपका ही एक सोल्यूशन में मैंने वो निकाला था कि एक इंफॉर्मेशन का लॉस हो रहा है कि वो अंदर है कि नहीं. बट एक चीज़ ये हमें पता है, एक चीज़ हमें पता है कि हम इसको तभी रीच कर पाएंगे अगर हम इसको रीच कर पाएंगे. I2 इसके लिए जब हम कंसिडर कर रहे हैं तब हम J1 को तभी रीच कर पाएंगे अगर हम J2 को रीच कर पाएंगे. देयर ओनली एक्चुअली 3 पॉसिबिलिटीज. I2 कह सकता है कि मुझे J1 और J2 में से किसी को भी नहीं पता, लाइक कोई भी I1 और I2 के बीच में नहीं आता है. दूसरा है कि सिर्फ J2 आता है. तीसरा है कि सिर्फ लाइक बोथ J1 एंड J2 आता है. इज इट क्लियर? दीज आर द ओनली 3 पॉसिबिलिटीज. जब हम सामने वाली चीज़ों को देखेंगे तो विद रिस्पेक्ट टू J1 एंड J2 ऐसा कभी नहीं होगा कि J1 सिर्फ आएगा. हो सकता है कि कोई नहीं आएगा, नहीं तो J2 आएगा, नहीं तो बोथ J1 एंड J2 आएगा. राइट? यहां से सोचिए, इट शुड बी एक्चुअली वेरी क्लियर, वेरी सिंपल. नाउ व्हाट विल वी डू? व्हाट विल वी डू? विल से कि अगर एम्प्टी है तो इसमें 0 बैठा देते हैं. 0 आना चाहिए इस केस के लिए, राइट? अगर J2 है, सिर्फ J2 है, तो क्या आना चाहिए? 1 आना चाहिए. और अगर J1 J2 दोनों है, अगर J2 I2 के बाद हो तो हाँ, मैं क्या डिस्कस किया कि इधर अपना J2 है, इसके बाद हम I2 में जाएंगे. तो J2 में मैं ये डिसाइड कर रहा हूँ कि हमें जब J2 मिलेगा तो हम क्या स्टोर करेंगे ताकि सामने वाले I2s के लिए प्रॉपर इंफॉर्मेशन रहे. सो माई the way I am actually setting this nomenclature is on the basis of this statement, J2 is less than I2. So this is a standard thing. ये कुछ ऐसा है, देखिए, something like this. मैं जब ये अपडेट किया था, मैं किसके लिए किया था? मैं सामने वाले जो एंड हो रहे हैं उनके लिए किया था. जो पहले एंड हो चुके हैं उनको तो फ़ायदा नहीं होगा इससे, तो इसलिए मैंने ये अपडेट किया था ताकि सामने वालों की हेल्प हो. सो दैट इज़ व्हाट आई एम फोकसिंग ऑन, कि हमें यहाँ भी कुछ ऐसा करना है, इधर कुछ अपडेट करना है ताकि सामने वालों को परफेक्ट इन्फॉर्मेशन मिले. तो सामने वाले पे फोकस करते हैं, जो सामने एंड होगा, जो हमारे सामने एंड होगा, हमारे एंड होने के सामने, उसके लिए क्या क्या पॉसिबिलिटीज़ है कि हमारे स्टार्ट या एंड कुछ भी नहीं आएगा, हमारा सिर्फ एंड आएगा, और तीसरा पॉसिबिलिटी हमारा स्टार्ट और एंड दोनों आएगा. These are the 3 possibilities. The 4th possibility is not there, कि हमारा स्टार्टिंग आएगा और एंड नहीं आएगा. Is this part clear? Maybe I should not just shoot on these kind of things. I understand that it takes time. So what I've just said is that whenever I face a second occurrence of something, I will update something. I'll update J2 and J1. I'll update J2 and J1. किसके लिए? सामने जो भी I2 है उनके लिए. सामने जो भी I2 पड़े हैं, जो शायद अपने पीछे देखेंगे रेंज में कि कौन कौन आता है, तो इस I2 के लिए क्या पॉसिबल है? एक ऐसा कुछ पॉसिबल है I1 इधर से लेकर इधर तक, फिर कुछ भी नहीं आएगा, J1 J2 में से कुछ भी नहीं आएगा। दूसरा पॉसिबिलिटी है कि J2 ही सिर्फ आएगा, और तीसरा पॉसिबिलिटी है कि J1 J2 दोनों आएगा। मेक सेंस? Then that is done. Then what we can say is, if we have J1 J2, then what should be the answer? It should be 0. ये होना चाहिए। ये होगा कैसे ये हमें नहीं पता, बट ये होना चाहिए। आपको ऐसे ही प्रोसीड करना है। क्या करना है उसके लिए क्या छोटा सा चीज़ करेंगे। सो आपको कुछ नहीं होगा तो 0 होना चाहिए, J2 होगा तो 1 होना चाहिए, J1 और J2 होगा तो 0 होना चाहिए। तो अगर सम सेगमेंट्री मेंटेन करेंगे, अगर एक सम सेगमेंट्री मेंटेन करेंगे, तो व्हाट इज़ द अप्रोच? बेसिक अप्रोच कि J2 के जगह हमें 1 बिठाना है, राइट। और सम सेगमेंट्री के लिए हमें क्या पता है, कुछ नहीं रहेगा तो 0 तो ठीक है, और J2 रहेगा तो इसके लिए 1 है, J1 रहेगा तो 0 आना चाहिए। तो सिंपल लॉजिक क्या कहता है, J1 जहाँ पे उसको क्या कर दो, -1 कर दो, राइट। J1 को कर दो -1, J2 को कर दो 1, और फिर क्या हो जाएगा, ये वाला रेंज अगर कभी आपने क्वेरी किया तो ये 1 और ये -1 कैंसिल हो जाएगा, एंड शैल यू गेट 0 फॉर दिस। दैट्स इट। एनी डाउट्स? Yeah. सोचना इन सब पे, मज़ा आएगा। सो मे बी दिस अ वेरी क्लासिकल क्वेश्चन, तो ये कर लेते हैं। क्वेश्चन शायद आप लोगों ने देखा भी होगा, या इस टाइप का क्वेश्चन। कोड फोर्सेस 474E pillars. So for I2 we will query in range of I1 plus 1 से I2 minus 1, exactly. We'll query in the range of I1 plus 1 से I2 minus 1. We will ask what is the sum. That's it. So anyway, let's discuss this question. I think, yeah, this is the question. You can open this link in your own devices as well. Read the question. Yeah, exactly. DP plus segmentary, you can actually call this topic. This is actually similar to LIS kind of a problem. LIS में it is actually a different version of LIS. LIS में ऐसा बोलते हैं कि HI should be less than HJ, but here we have just changed the condition. That's it. From I we will consider all J where we can jump, then we will choose the one with maximum answer. Exactly. So we need those pre-computed values. कहाँ कहाँ जंप कर सकते हैं, but what about the rest? Same feeling? Since difference is D, difference is D. Think about it. I actually want a very good amount of implementation details from all of you. कैसे इसको implement करेंगे? Actually, like everything can be written in just 2-3 lines. We need all values from I in between I minus D and I plus D to I and I minus D and I plus D to I actually right. So even I read that wrong. Okay, so the distance has to be greater. So in between I and I minus D, is it? Or we can say something like maybe, what can we say? The distance has to be greater than equal to D, which means it will be from minus infinity, or maybe we can say from 1, h minimum value is 1, so from 1 to hi minus d minus 1 maybe, and what else? Okay, we are at j, suppose. So at j we want to see that which is the I we can come from. Suppose this is how we are proceeding. Or do you want to say the other way, that from I where all you can go? That is going from left to right. You can actually choose it. Not distance but higher. ठीक है? hi minus d and hi plus d. No, the distance has to be greater than equal to d. The difference between the distance has to be greater than equal to d. So it cannot be between those two things. It has to be either in the first half or in the last half. Right? So if basically if this is your h, if this is your hi, and if you want to see what is the hj I can come from, maybe, or from this what hj I can go to, what j I can go to. So it should happen that in the number line, this is hi minus d and this is hi plus d. So you'll basically have this part of the number line and this part of the number line. Okay, in the correct range. Over here you can say that I want the maximum and those things. So yeah, this is basically a DP problem, and over here you can say DPI equals to for all I know j is basically greater than I think, right? I is less than j. Yeah, j is greater than I, so what can you say? Summation from k equals to I plus 1 to n. I want to see that what is dp of j plus 1. I'm sorry, not summation, this is basically maximum. We want to find the maximum of dp j plus 1 if h of j satisfies this. Okay, h of j satisfies this, else we will have 0 else. Okay, so this is the function, and this is we are finding the maximum in this range. I hope it is clear. I made the same mistake actually. While actually telling with what you wrote, I found it that okay, it's the opposite way. So this is exactly what we have to do. This is the DP thing, and the problem is that if n would have been about 10,000, it would have been pretty easy. Like you would have done an n square kind of algorithm. 1,000, 5,000, an n square algorithm would have done. But over here the trick is different. It has been given that n can go up to 10 to the power 5, I guess. n can go up to 10 to the power 5. What this basically means is we cannot iterate through all the j's. We cannot iterate through, I'm sorry, why I have written j over here. Okay, you can actually replace this by j. There you go. So j equals to I plus 1 to n, basically dp is j plus 1. You have to find out for all the j which are pertinent to this. You cannot use any formula over here because it refers to a certain range. You have to apply some property of these ranges, similar to what is exploited in segmentaries. Okay. So how can we go about it? Can you see that these are certain values, and you can simply make use of a max segmentary because it is a contiguous range. You have to find the maximum value over here. So can you just say, okay, I want all the dp values lying in this range or maybe these ranges, okay, something like this. So there are two ranges. First of all, the range of these indices. Second is the range of these h values. Both ranges are important, and this is also a trick. Unless you're without thinking, you apply the exact algorithm. I feel we need to use segmentary for minimize the function max from linear to log. Yeah, definitely max definitely performs it. You want the maximum value in a certain range, you use the segmentary so that that linear traversal to find the maximum value can be rather improved to a logarithmic traversal. That part is absolutely fine. What else? अब हमें क्या चाहिए, किसी भी i वाले पॉइंट के लिए हमें क्या चाहिए, हमें चाहिए इस रेंज में j इक्वल्स टू i प्लस 1 से n, और साथ में हमें ये भी चाहिए कि एच जे उसका वैल्यू यहाँ से यहाँ तक होना चाहिए, डी पी ऑफ एच ऑफ आई माइनस डी से डी एच ऑफ जे, जो भी हो, माइनस इन्फिनिटी से वो वहाँ से प्लस इन्फिनिटी. सो वी आर इंटरेस्टेड इन दीज रेंजेस, this range and this range. That also we need to check. So there are two different ways in which ranges are defined. One is this way, indexes, another is this way. Can we simplify this? Because this is difficult. This is indeed difficult. If you have two different values, ai and aj, and you have to do something for those values where ai's range is something and bi's range is something, that is really difficult. Why it is so? Because on what will you construct the segmentary? Will you construct it on the basis of ai or on the basis of bi? That is what makes it difficult. But again, you can think of simplifying one part of it. You can think, okay, these are two things, h of something and another is from here to here. One of them can be ignored. You can think in that manner, because in the previous problem also we used many tricks. I told you the answer, otherwise you may have stayed for maybe some 6 or 7 hours thinking on it. So, or maybe it's not that big a problem statement. Usually we keep on thinking if the problem statement is large, it makes us think longer. But these were the things I utilized when I reached the answer in the previous question. The precise thoughts were, there are various ranges, but over here what did we do? हमने क्या किया था इंटरसेक्टिंग सेगमेंट्स में? हमने कुछ ऐसा कहा था कि J2 ऑलरेडी जो है, हमने कुछ मतलब assumptions यूज़ किया था कि हम इसी डायरेक्शन में चल रहे हैं, तो I2 डेफिनेटली J2 के बाद ही आएगा. हम ऐसे ही पढ़ रहे थे. तो सिमिलर चीज़ अगर हम यहाँ पे यूज़ करेंगे, हो सकता है हमारे रेंजेस काफ़ी आसान हो जाए, हमारे एनालिसिस. So I will tell the precise answer. I'll provide half a minute for you to think and tell which of these can be avoided and how it can be avoided. This is one range and this is another range. I want only those values for which both the ranges are satisfied. So which of them can be avoided and how? What range I'm referring to here, it is something like this. Age j is less than hi minus, less than equal, I think, less than equal hi minus d. Okay, then this is closed. I think I forgot that this is closed. And please do point out if you notice any mistakes of this kind, because many people might be watching recordings and they might, we never know, like he can't reach out to me, right? or you can say either this or this. So this is the condition. This is one range, or in union of two ranges. For both I can say log n, very intuitive kind of chemistry. Over here I know this is a completely different thing. I need the sort of intersection of all the elements. But that's not an easy thing. Which of them can be avoided? So it turns out, okay, my video is in top right. Okay, so what I wrote over there is nothing but what I wrote is something like this. J is less than equal to Hi minus D, or Hj is greater than equal to Hi plus D. But are you not getting any ideas? Anyways, let's discuss. What do we know? कि I के लिए इस फॉर्मूला के हिसाब से I के लिए I plus 1 से n भी n ही ज़रूरी है, पिछले वाले वैल्यू ज़रूरी नहीं है. So what we can say, for I equals to 5, we can say that from I equal to 6 to last I, only those values are important. For I equals to 4, 5 से लेकर last तक वो important है. For I equals to 3, 4 से लेकर last तक वो important है. So what can we say? Our approach can be simply something like this. We can simply say that okay, I equals to n minus 1 के लिए पहले कुछ एक डिफ़ॉल्ट वैल्यू कुछ डाल देते, फिर नेक्स्ट वाले के लिए देखते, फिर नेक्स्ट वाले, ऐसे करके. बिकॉज हमें क्या पता है कि इस आई को बस इन्हीं की ज़रूरत पड़ेंगे. सो इन सब के लिए तो ज़ीरो ही रहेगा इनिशियली, दैट्स इट. तो इसके लिए हम क्या बता सकते हैं, इसकी ज़रूरत पड़ ही नहीं रहा है. ये सॉर्ट ऑफ लाइक वी आर एबल टू take care of it intuitively. We are only interested in affirming the range for this. We keep previous values, yeah exactly, we can like सारे इनिशियली सब कुछ ज़ीरो है, इनिशियली कोई भी पिलर नहीं है, कुछ नहीं है. अब क्या हमें चाहिए? अब हमें चाहिए कि अब एक्चुअली ओके हाँ सो नॉट ज़ीरो, एक्चुअली इट शुड बी केप्ट एज 1. वाई? अगर कोई कुछ नहीं रहेगा तो 1 होगा, राइट? ये खुद बैठेगा तो 1 आ जाएगा डीपी ऑफ आई में. मूविंग अहेड, व्हाट डिड आई डिस्कस? समथिंग लाइक दिस, दैट यहाँ पे मुझे क्या चाहिए? मुझे चाहिए सम क्वेरी. मैं क्या करना चाहता हूँ? क्वेरी फॉर डीपी ऑफ टी such that it satisfies the height criteria. T should satisfy the height criteria. तो कैसे कर सकते हैं? हम सिंपली ऐसे ही कर सकते हैं, जो भी हाइट्स हमें इधर मिलेगा वही हम मतलब उन सारे हाइट्स में हम स्टोर करेंगे. हम यही कहेंगे कि इसके हाइट में, सेगमेंट ट्री में हम चलते हैं, इसका हाइट अगर है 100 तो हम 100 वाले नोड में चलते हैं, 100 वाला जो लीफ है वहाँ पे चलते हैं, उसके सारे एंसेस्टर्स में ये अपडेट भी करेंगे. वहाँ पे हम जाके बोल देंगे कि हाँ इसके लिए मैक्सिमम हमें मिल रहा है, वॉट एवर द वैल्यू इज़ द मैक्सिमम, जो भी इसका डीपी है, डीपी ऑफ वॉट एवर इट इज़, राइट? तो ये हम कहाँ जा रहे हैं? 100 इज़ वॉट? 100 इज़ द एच ऑफ जे. 100 इज़ द एच ऑफ जे. हम 100 में जाके स्टोर कर रहे. अब हम क्या बोल सकते हैं? बस यहाँ पे क्या सर्च करना है? ये सर्च करना है कि इसका अगर हाइट है हमारा 50, तो हम बोलेंगे 51 से लेकर इन्फिनिटी तक जो भी सेगमेंट्री जहाँ तक स्टोर कर रहा है वहाँ तक ये बताओ कि मैक्सिमम कौन सा है. मैक्सिमम लेके मुझे दे दो, जो भी है मैं उसके साथ +1 कर लूँगा. मेक सेंस? वी कीप प्रीवियस वैल्यूज एज 0, डेफिनेटली 0. Why int max? We are maximizing, right? Any questions till now? So we use height as index in point update, exactly. So height is used as the index. Height is used as the index. हाइट में जाके हम बोल रहे हैं तुम इधर डीपी वाला वैल्यू रख दो, फिर हम बोलेंगे हाँ इस हाइट से इस हाइट तक मुझे बताओ, और इनिशियल उस हाइट से उस हाइट तक मुझे बताओ. सॉरी इन्फिनिटी तो नहीं, इस पार्ट में और इस पार्ट में मुझे, हाँ इन्फिनिटी एक्चुअली, इस पार्ट में और इस पार्ट में मुझे बताओ कि कौन से लाइक व्हाट इज द मैक्सिमम, देन आई विल कंबाइन, आई विल टेक द मैक्सिमम ऑफ बोथ ऑफ देम. मेक सेंस? So this is my update operation where I'll go to the height and I'll tell that okay, this is the max, and that is a different operation. So you can have multiple as well, like for the same height you can have multiple entries, so you'll store the maximum over here and similarly you'll be updating. Make sense? We are traversing from right to left according to your algorithm. मैं आपके algorithm के हिसाब से ही चला हूँ. अगर मैं करता तो मैं शायद लेफ्ट टू राइट चलता, बट इस केस में हाँ हम राइट टू लेफ्ट चल रहे हैं. हम राइट टू लेफ्ट चल रहे हैं क्योंकि राइट के केस में हमें बेस केस पता है कि देयर इज़ नथिंग. फिर हम लेफ्ट की तरफ आ रहे हैं, बेस केस की ज़रूरत नहीं है, हम सेगमेंट्री को एक्चुअली जीरो से स्टार्ट कर सकते हैं. इफ़ वी वुड हैव डन फ्रॉम लेफ्ट टू राइट, देन वी वुड हैव डन एग्जैक्टली द ऑपोजिट थिंग. एक्चुअली सेम ही होता है. इवन इफ वी वेंट फ्रॉम लेफ्ट टू राइट, द रेस्ट ऑफ द एल्गोरिथम वुड हैव बीन सेम. We initialize all the elements to 1. Which elements? Okay, एक बार लेफ्ट टू राइट, ठीक है. लेफ्ट टू राइट अगर चलना हो तो क्या होगा? डी ऑफ हमारा राइट में कौन है? जे है, तो हम क्या बोलेंगे? ज़ीरो इंडेक्स्ड है तो हम बोलेंगे समथिंग लाइक दिस कि मैक्स ऑफ जो भी आई लाई करता है ज़ीरो से लेकर जे माइनस वन तक, उन सब के लिए डी ऑफ आई को कंसीडर करो इफ़ वो कंडीशन सेटिस्फाई करे कि एच ऑफ आई माइनस एच ऑफ जे लेस देन इक्वल टू, अच्छा ये ऊपर जा रहा है तो आई एम राइटिंग नथिंग डिफरेंट, दिस हाइट इज लेस देन ग्रेटर देन इक्वल टू डी, ग्रेटर देन इक्वल टू डी, एंड दिस विल बी ज़ीरो, अदरवाइज जो भी ये वैल्यू होगा दिस वैल्यू प्लस वन. ओके, दिस वैल्यू प्लस वन. दिस इज आवर आंसर. हम क्या बोलेंगे कि फ्रॉम j इक्वल्स टू ज़ीरो से लेकर j इक्वल्स टू n माइनस वन तक जाएंगे. ठीक है. ग्रेट. वही सप्लीमेंट्री क्वेश्चन था, इसके लिए क्या करें? रेंज है स्टिल 10⁻15, तो ये डीपी भी स्टोर करना थोड़ा मुश्किल है. तो क्या करें? एक तो हम सेगमेंट्री में मेंटेन कैसे कर रहे हैं? सेगमेंट्री में ये आप बोल सकते हैं कि डीपी ऑफ एच जे के हिसाब से स्टोर हो रहा है. इट इज़ समथिंग लाइक डीपी ऑफ एच जे, बट यू शुड नॉट एक्चुअली से लाइक दैट. यू शुड एक्चुअली से समथिंग लाइक डीपी ऑफ एक्स. इन योर सेगमेंट्री एवरी नोड हैज़ अ सर्टेन वैल्यू. आप वो नोड का वैल्यू यूज़ कर रहे हैं. दिस इज हाउ यू डू इट. तो वहाँ भी आप क्या करते हैं? अगर कुछ इंटरनल नोड में आप है, वो क्या डिपिट करता है कि उस सब ट्री में आपका मैक्स क्या है, तो आप उन मैक्स को कंबाइन करते हुए आगे बढ़ते कि लेट अस फाइंड आउट द बेस्ट मैक्स आउट ऑफ देम, मैक्सिमम ऑफ ऑल द मैक्स. सो एग्जैक्टली हमें क्या पता है? दिस एच आई, ये जो एच आई एक्स क्या हो सकता है? एक्स आपका जा सकता है 4n तक, एंड व्हाट इज n? 4 into n, and what is n? n basically can go up to 10⁻15, क्योंकि एच आई को हम इंडेक्सेस के हिसाब से यूज कर रहे हैं. सो दिस इज हाउ इट लुक्स लाइक 10⁻15, राइट? 4 into 10⁻15. व्हाट मोर? हमें ये पता है कि द नंबर ऑफ यूनिक हाइट्स, वो डेफिनेटली जो यूनिक हाइट्स है, नंबर ऑफ यूनिक हाइट्स वो कितने हो सकते हैं? मैक्सिमम 10⁵. तो हम वहाँ पे सीधे सीधे मैपिंग लगा सकते हैं. हम बोल सकते हैं कि अगर ये तुम्हारे हाइट्स हैं, दीज आर योर हाइट्स 100, 300, 200, 250, 350, ऐसा कुछ, तो हम बोल सकते हैं यूज समथिंग लाइक दिस, मे बी 150. हम बोल सकते हैं इस तरीके से इसको लिखेंगे, 100, 150, 200, 250, 300, 350. हम बोलेंगे दिस इज एलिमेंट 0, दिस इज एलिमेंट, और मे बी हाइट्स हम लोग कहाँ से लेते हैं? सपोज 1, ये 2 है, ये 3 है, ये 4 है, ये 5 है, ये 6 है. अब ऑर्डर में रख देते हैं। 100 के लिए क्या है 1 है, 300 के लिए क्या है 300 के लिए 5 है, 200 के लिए क्या है दिस इज 3, 250 के लिए 4 है, 350 के लिए 6 है, 150 के लिए 2 है. So this is exactly what is coordinate compression. Okay. It is e problem otherwise. ठीक है, कोऑर्डिनेट कंप्रेशन इज नॉट अ बिग डील. वो मैं कोड दिखाया था, आप पिछले क्लासेस में जा सकते हो, खुद भी ट्राई कर सकते हैं. यू बेसिकली हैव टू इटरेट थ्रू ऑल द वैल्यूज एंड यू हैव टू स्टोर इन अ मैप कि 100 हमारे लिए क्या है 1 है, 200 हमारे लिए क्या है समथिंग लाइक दिस. एंड देन और क्यों मैं इसको सॉल्व कर रहा हूँ, इसका एक रीज़न ये है कि मान लीजिए मैं चाहता हूँ 250 के लिए, ये देखना कि -100 और +100 समथिंग लाइक दिस. तो मैं चाहता हूँ कि 150 के नीचे या फिर 350 के ऊपर मुझे चाहिए, 150 है उसके नीचे और 350 है उसके ऊपर मुझे ये एलिमेंट्स चाहिए. तो मैं क्या करूँगा, मेरे पास तो ये स्टोर्ड है, मेरे पास तो 100 200 ये सब स्टोर्ड ही नहीं है, सेगमेंट्री जानते ही नहीं है 200 300 ये सब क्या है. मैं ये बोलूँगा यहाँ पे बाइनरी सर्च करूँ. 150 के करस्पॉन्डिंग एलिमेंट क्या है, इट इज़ 2. व्हाट विल वी फाइंड, द एलिमेंट ग्रेटर देन इक्वल टू दिस पर्टिकुलर पोजीशन. तो अगर हमने 140 दिया, 140 के लिए ढूंढने दिया, तब भी ये 2 ही देगा. अगर हमने 160 दिया तब ये 3 देने वाला है. ठीक है, तो हम बोलेंगे कि हाँ इस टारगेट वैल्यू से जस्ट बड़ा या इक्वल वैल्यू कौन सा है हमारे सेगमेंट ट्री के इंडेक्सेस में. और फिर हम बोलेंगे ओके सो एक सेकेंड, आई थिंक देयर इज एन इशू नाउ. ओके जस्ट वेट अ बिट, मेरा चार्ज वो 2% में आ गया है. आई जस्ट फेच अ चार्जर एंड देन विल कंटिन्यू. एनी क्वेश्चंस यू हैव यू कैन आस्क. Okay. Yeah. Okay. Now I can breathe. So where are we? We can find out the limits, and over there we can actually go carry it out. Okay. So binary search, how long will that take? Login, and then that query that will also take login. So we are done. Not login. Here it will take log of. Yeah, there also it will take login because number of elements over here, that is also n or 4n, whatever you say in segmentary. Okay, 2n or 4n basically. Any doubts? Hope there is none. Do you want discussion on 2D segmentary? Because we don't have much time. Do you want any discussion on 2D segmentary? Do you want to just know how it looks like? Or we will end with maybe another simple problem. Simple means a problem of this kind. We can either discuss a bit around थोड़ा overview. ठीक है, okay. थोड़ा overview discuss कर लेते हैं 2D segmentary. ओके 2D segmentary कुछ ऐसा है, जब सिंपल प्रॉब्लम होमवर्क में दे तो ऐसा हो तो हाँ, सिंपल प्रॉब्लम इज समथिंग लाइक दिस. सपोज यू हैव एन n क्रॉस m मैट्रिक्स में भी n क्रॉस m, इसमें कुछ वैल्यूज़ है और बेसिकली कितने सेल्स है, n क्रॉस m सेल्स है. और हम लोग बोल सकते हैं कि एक टाइम पे लाइक किसी एक पर्टिकुलर सेल को अपडेट करो. सो द अपडेट ऑपरेशन इज अपडेट. Suppose this is A matrix, so update A of ij. So you have to update aij. And another thing is sum का example लेता हूँ. sum max कुछ भी आप ले सकते हो. The only difference is 2D. तो आपको बताना है कि from certain I1, I1 J1, I1 J1 to certain I2 J2. This is something like I2 J2. What is the summation of this entire matrix? Okay, what is the summation of all the values in this matrix? 1D में फ्लैटन कर देंगे तो क्या होगा? ये आ जाएगा, फिर ये वाला पार्ट नहीं रख सकते, फ्लैटन करेंगे तो डेफिनेटली ये करेंगे, फिर उसके बाद ये करेंगे, फिर उसके बाद ये करेंगे, ऐसे कुछ करेंगे, राइट? ऐसे कुछ करेंगे तो कैसे आ जाएगा? पहले ये पोर्शन आएगा, पहले ये पोर्शन आएगा, ए बोल रहा हूँ इसको, सॉरी समथिंग लाइक x1 बोल रहा हूँ इसको, फिर ये पोर्शन x2, फिर ये पोर्शन x3, फिर ये पोर्शन x4, फिर ये x5, फिर ये x6, समथिंग लाइक दिस। ये ऐसे लगातार ऐसे लाई करेगा, x3, x4, x5, x6, x5, x6। तो इस समय अगर हम बोलेंगे ठीक है हमें दे दो इस पार्ट का, तो हमें पहले x1 के लिए करना पड़ेगा, फिर x4 के लिए, फिर नेक्स्ट के लिए x7 के लिए, एंड ये हाँ, तो पूरा कितनी बार करना पड़ेगा? नंबर ऑफ रोज कितना हो सकता है? n। सो वो n टाइम्स हो गया, n टाइम्स हम बोल सकते हैं ठीक है कितना ऑपरेशन है, log m, n टाइम्स log m पर अपडेट, और पर सम में भी, हाँ पर सम। 0 0 से LR पूरा लेंगे, हाँ 0 0 से LR पूरा लेंगे, फिर माइनस करेंगे, ठीक है वो भी अगर कर ले, माइनस किसको करेंगे? लाइक इस पूरे का सम ले लेंगे, फिर किसको माइनस करेंगे? ये भी एक कंटिग्यूअस सा ही चीज़ है जो आप इधर देख रहे हो या इसके लेफ्ट में, ये सब 2D फॉर्म में है, एंड आप अगर इसको लीनियराइज करने जाओगे तो इट वॉन्ट स्टे द सेम, राइट? इज इट कन्विंसिंग? लीनियराइज करेंगे तो ऐसे कुछ आएगा, x1, x2, x3, x4, ऐसे कुछ, x1 इधर है, x2 इधर है, फिर x3 नेक्स्ट लाइन, फिर x4, तो x2 और x3 बाहर है, तो आपको वो ढूंढना पड़ेगा कब जाके किस रेंज में क्वेरी करेंगे। इसका मतलब कितने सारे क्वेरीज होंगे? दिस इज वन क्वेरी, दिस इज अनदर क्वेरी, दिस इज अनदर क्वेरी ओवर हियर x7 जो कि इधर रहेगा x7, ऐसे करके जो शायद इसके अंदर रहेगा। तो ऐसे हम बोल सकते हैं काफ़ी सारे क्वेरीज हो जाएंगे। हाउ मेनी क्वेरीज कैन टेक दिस? जितने सारे रोज हैं, दैट इज द लॉजिक दैट आई एम अप्लाइंग। सो कैन यू सी दैट linearizing can't directly help? So in 2D segmentary there are two things that we perform. One is update aij, another is find the sum, the summation for I equals to I1 to I2, j equals to J1 to J2, summation of a I1 J1। हाँ आप पढ़ते हैं, रेक्टेंगल के ऊपर में जितना है वो एक साथ सम निकाल के माइनस कर देंगे, ठीक है? तो आप बता रहे हैं कि ये वाला हम निकाल देंगे, वेरी गुड, ये वाला डायरेक्टली हम निकाल देंगे, और आप बोल रहे हैं कि ये वाला निकालेंगे, सर शायद आप ऐसा कुछ बोल रहे हैं कि यहाँ तक हम निकालेंगे। तो आप थोड़ा सोचिए इस पार्ट के बारे में जो मैं येलो में मार्क कर रहा हूँ, इस पार्ट को कैसे हटाएं और इस पार्ट को कैसे हटाएं, राइट? मेक सेंस कि उतना ट्रिवियल नहीं है इसको हटाना। ये सेम कंसेप्ट आ रहा है इधर कि लीनियराइज जिस तरीके से किए हैं, लीनियराइज करने पे बेसिकली हमारा नॉन कंटिग्यूअस फॉर्म हो जा रहा है, यही एक इंपॉर्टेंट चीज़ था। हम उधर कंटिग्यूअस रेंज के लिए बता रहे थे, कुछ भी कंटिग्यूअस रेंज दे दो हम लॉग इन टाइम में निकाल देंगे। यहाँ पे क्या हो जा रहा है, अलग अलग अगर हो जाएगा तो अलग अलग क्वेरीज करना पड़ेगा हमें, वी कांट हेल्प इट। येलो वाला डिफिकल्ट है, एंड यू कैन एक्चुअली से दैट sorry just a second, okay, you can actually say that ये येलो वाले पार्ट का डिफिकल्टी इज द सेम एज ये बीच वाले पार्ट का डिफिकल्टी। तो बेकार में माइनस उसके तो झंझट में नहीं जाएंगे, हम बीच में इसी पे फोकस करेंगे, इसका कैसे निकालते हैं। तो इसके लिए हम बेसिकली 2D सेगमेंट्री अप्लाई करते हैं, बिकॉज 1D सेगमेंट्री डजंट रियली हेल्प अस ओवर हियर। 2D सेगमेंट्री में हम कुछ ऐसा बोलते हैं कि these are our nodes. टू डायमेंशनल मतलब क्या है? 2D एरे क्या होता है कि एक 1D एरे में हर एक एलिमेंट एक 1D एरे है. दिस इज हाउ प्रोबेबली यू आर टॉट इन कॉलेजेस, maybe not in schools, but yeah, even in schools I think that is the way they introduce it nowadays. So every node now not only contains one element, but ये ऐसा कुछ बताता है कि ये पूरे सॉर्ट ऑफ एक रो का इंफॉर्मेशन स्टोर कर रहा है. एक रो में या फिर ऐसा कुछ आप सोचिए कि ओवर सर्टेन रोज, ओवर सर्टेन में भी एक लीफ के बारे में डिस्कस करते हैं. ये एक लीफ है. लीफ मतलब ये इंडिकेट कर रहा है समथिंग लाइक दिस, x इक्वल्स टू मे बी व्हाट डू वी नो 1 2 3 4 5 6, तो डेफिनेटली 4 होगा. और इसका क्या रहेगा? समथिंग लाइक 0 to 0. 0 to 0, दिस इज बेसिकली सेगमेंट्री में हम ऐसा कुछ लिखते हैं 0 से 0 तक जा रहा है ये वाला नोड. तो दिस इज द इंडेक्स फॉर द रो. रो 0 से 0 तक ये पूरा इंफॉर्मेशन स्टोर कर रहा है. तो एक ये कितना है? 4 है. तो हम 4x4 का एक विजुअलाइज करते हैं. 4x4 में बेसिकली ये जो जिम्मेदारी है, इस पार्ट का जिम्मेदारी हम सौंप रहे हैं इस नोड को, इस पूरे नोड को. कैसे? सिंपल सेगमेंट्री की तरह हम बोल रहे हैं कि ये भी, क्योंकि इसमें 4 एलिमेंट्स हैं तो इसमें ऐसे एक सेगमेंट्री रहेगा. ठीक है. सिमिलरली यहाँ पे हमारा क्या रहेगा? सिमिलर एक सेगमेंट्री जो किसको डिनोट करेगा? द सेकेंड रो. The second row will be denoted by this part. Then if we try merging it, कि मैं इन दोनों का एक साथ चाहता हूँ, इन दोनों का मैं चाहता हूँ टोटल सम मैं चाहता हूँ रूट में, एंड सो ऑन, तो कुछ ऐसा बनेगा. अब समझा रहा हूँ कि इसका एक एक का मतलब क्या है. इस पार्ट, पहले पार्ट का मतलब क्या है? इन दोनों एलिमेंट्स को जोड़ के जो मिलेगा वही है पहले पार्ट का मतलब. नेक्स्ट पार्ट, इसका मतलब क्या है? इन दोनों एलिमेंट्स को जोड़ के जो मिलेगा. तो इसका मतलब क्या बना? इस पार्ट का मतलब क्या है? ये वाला नोड क्या स्टोर करेगा? ये चारों नोड्स जोड़ के जो बना. तो ये देखिए 2 लेवल्स में हो रहा है. 2 लेवल्स में हो रहा है क्योंकि ये वाला लेवल, ये जो अंदर पे है, अंदर जो y के बेसिस पे ये जो लेवल है वो बता रहा है कि y में, सॉरी, ये जो कॉलम्स, हम किन कॉलम्स को मर्ज कर रहे हैं. और यहाँ पे हम बता रहे हैं, आई एम सॉरी, हाँ, यहाँ पे हम बता रहे हैं कि किन x को मर्ज कर रहे हैं. सो दिस ब्लू लाइन एक्चुअली टेल्स मी दैट व्हाट इज अ कॉम्बिनेशन ऑफ रोज, combination of rows, and within this structure every node tells me the combination of columns, right? तो मैं क्या कर सकता हूँ? रोज, कौन कौन से रोज से मेरा ये टारगेट जो रेंज है वो बनेगा, उसके लिए मैं ब्लू इन नोड्स को टारगेट कर सकता हूँ. ठीक है, शायद ये वाला और ये वाला. फिर मैं उनके अंदर जाके कलेक्ट कर सकता हूँ कि कौन सा रेंज मेरे लिए इंपॉर्टेंट है. ड्रीम विद इन ड्रीम, इंसेप्शन जैसा हो गया. अगर हर एक रो के लिए एक सेगमेंट्री रखें, राइट, दैट इज एग्जैक्टली द आइडिया. सो एग्जैक्टली कुछ ऐसा है. कितने सारे टोटल आपके बनते हैं? हमें क्या पता है टोटल नंबर ऑफ ब्लू वाले नोड्स कितने बनेंगे? बड़े वाले नोड्स 4n जैसे होता था, मैक्सिमम 4n, 2n में यूजुअली हो जाता है. अब हमें क्या पता है दूसरे वाले पार्ट के लिए? ये जो अंदर बनेगा, हर एक के अंदर ऐसे बनेगा, कितने सारे बनेगा? 4n. सो व्हाट कैन वी सी? n क्रॉस m तो हमारा इनपुट साइज था, इट इज नथिंग बट 16 mm. गॉट इट? दिस इज द इनपुट साइज, सॉरी, दिस इज द साइज ऑफ द सेगमेंट्री. बिल्ड करने के लिए कितना कितना लगना चाहिए? सिमिलर. अब कैसे बिल्ड करेंगे? इट नीड्स टू बी आंसर्ड. तो अगर वो थोड़ा देखना है तो इट इज़ नथिंग बट समथिंग लाइक दिस, कि मान लीजिए आपको ये वाला बिल्ड करना है, ये वाला बिल्ड करना है, तो कैसे बिल्ड कर सकते हैं? आप इसके लिए क्या बोल सकते हैं कि इसके लिए मैं अपने कॉलम्स के जो जूनियर से उन तक पहुंच जाता हूँ, जो मेरे एक कॉलम को, मतलब कॉलम्स की इंडिविजुअली रिप्रेजेंट करते हैं. मैं इनसे निकाल लेता हूँ, मैं इनसे निकाल देता हूँ और इनसे निकाल देता हूँ. दीज आर द 2 वैल्यूज दैट आई कैन कलेक्ट एंड आई कैन गेट इट. बाकी सब के लिए मैं क्या कर सकता हूँ? अगर ये लीफ है, इसके लिए मैं क्या बोल सकता हूँ? इसके लिए मैं बोल सकता हूँ सिंपल aij को पढ़ लो. a ऑफ इन दिस केस क्या होगा? व्हाट इज द x होगा आपका 1 और y होगा आपका 0, राइट. A10, right? I'm sorry, कुछ calls आ रहे हैं, I don't know, but I'll attend after this. I'll leave and connect once so that I don't miss any chats. हाँ, तो क्या है, हमें ऐसे इंडेक्स इधर मिल रहा है तो ये हम डायरेक्टली निकाल सकते हैं। ये हम कैसे निकाल सकते हैं? बाय मर्जिंग दीज टू। वाई? क्योंकि ये वाला एलिमेंट अगर आप थोड़ा सोचेंगे, टाइम थोड़ा बिताएंगे, A13 है और ये वाला एलिमेंट क्या है, A03 है। तो इनको जब आप कनेक्ट करेंगे आपको क्या मिलेगा, ये जो x है ये क्या डिनोट कर, ये डिनोट करता है कॉम्बिनेशन ऑफ द कॉलम्स, कॉम्बिनेशन ऑफ कॉलम्स, ओके सॉरी, कॉम्बिनेशन ऑफ रोज। ये ब्लू रिप्रेजेंट करता है कॉम्बिनेशन ऑफ रोज 0 एंड 1। तो आपको वो कॉम्बिनेशन मिल जाएगा 0 और 1 में, जो कॉलम 3 है उसके अंदर क्या है। अब दूसरा है कि आप अंदर वाला कैसे करें, सिंपल है। अंदर वाले के लिए आप क्या कर सकते हो, इसको अगर आपको भरना है तो आप कैसे करेंगे कंसेप्चुअली, या तो आप नीचे पहुंच जाएंगे इसके करस्पॉन्डिंग वाले के पास, आप बोलेंगे कि रोज में इसको तोड़ देते हैं, सॉरी हाँ रोज में, कुछ रोज के लिए मेरा लेफ्ट चाइल्ड कंटेन करता है, कुछ रोज के लिए मेरा राइट चाइल्ड कंटेन करता है। सो आई विल गो टू द लेफ्ट चाइल्ड एंड द राइट चाइल्ड, आई विल ऐड देम अप एंड आई एम डन। यह सब कर सकते हैं। दूसरा क्या तरीका है, दूसरा पैसे जा सकते हैं, इधर नीचे और इधर नीचे, राइट, ऐसे आप जा सकते हैं। बट हाँ, थोड़ा अगर थोड़ा दिमाग लगाए तो कौन सा बेटर है, डेफिनेटली, क्योंकि हमें पता है कि ए ऑफ आई जे, उससे अगर हमें 2j में जाना पड़े तो ये ईजियर है अनलाइक आई से 2i। क्यों? क्योंकि 2i बेसिकली वो जो 2D एरे का पहला इंडेक्स होता है वो और भी दूर पे लोकेटेड है, राइट, वो और भी दूर में जाना पड़ता है। और ये सब ओएस का कंसेप्ट है कि सेम ब्लॉक में लाई करेगा तो थोड़ा फास्ट होगा, नहीं तो वो सब आप देख लीजिए। बट एनीवे, ऐसा हम बेसिकली कह सकते हैं कि हाँ, जे से 2j में रीच करना इज ईजियर देन आई से 2i में रीच करना। ये कंपेटिव प्रोग्रामिंग में काफ़ी लोग यूज़ करते हैं और कभी कभी टीएलई से हम बच जाते हैं बाय यूजिंग दिस काइंड ऑफ आइडिया फॉर 2D एरेस। ठीक है, कंबाइन करने के लिए वापस सेक्ट्रीज में ट्रैवर्स करना होगा ना, वापस ट्रैवर्स नहीं करना होगा, कम्बिनेशन इज वन वे, लाइक ट्रैवर्स करेंगे बिल्ड ऑपरेशन जैसे होता है, नीचे वाला कैलकुलेट कर लो फिर ऊपर वाला नीचे के वैल्यूज को यूज़ करके कैलकुलेट कर लो। तो यहाँ भी हम वही करेंगे कि पहले कौन सा करेंगे, समथिंग लाइक दिस, पूरा नीचे जाएंगे, तो मैं ऑर्डरिंग बता रहा हूँ, पहले इसको फिल करेंगे 1, फिर इसको करेंगे 2, फिर इसको करेंगे 3, ठीक है, फिर ऐसे करेंगे, उधर जाएंगे, इधर फिल करेंगे 4, 5, 6, फिर ये 7, ये पूरा फिल कर लिया, फिर ऊपर जाएंगे। अब इसके लिए फिर ये वाला फिल करेंगे सेम सेम तरीके से। ये कहाँ से कहाँ तक जाएगा, बेसिकली ऐसे 8, 9, 10, 11 ऐसे करके 8, 9 बेसिकली ये 10 होगा, ऐसे करके कुछ होगा, एंड ये हो जाएगा 14 आई गेस। हाँ, तो फिर हम इधर आएंगे और हम बोलेंगे कि फिर हम इसको फिलअप करेंगे समथिंग लाइक दिस, और मे बी थोड़ा अलग भी नहीं, ऐसे ही करेंगे। फिर हम बोलेंगे कि अब इसके लिए हमें फिल करना है, अब इसके लिए हमें फिल करना है, ये जो अपना ब्लू है इसके लिए फिल करना है, तो इसके लिए हम एकदम लीफ में चले आते हैं। लीफ के लिए हम बोलते हैं अब इसको फिल करेंगे, कैसे, इन दोनों को लेके, फिर इसको फिल करेंगे, दिस इज 16, दिस इज ना 17, इसको कैसे फिल करेंगे, इन दोनों को यूज़ करके। दिस इज लाइक मैं ये टाइम स्टैम्प डाल रहा हूँ कि किसको कब मैं अपडेट करूँगा, तो इससे आपको आइडिया मिल जाएगा कि बेसिकली किस ऑर्डर में हम करेंगे। सो नाउ वी कैन सी दैट सारे ऑर्डर 1 ऑपरेशन है, सबके लिए ऑर्डर 1 ऑपरेशन, जिसके लिए भी मैं करना चाहूँगा, क्योंकि मैं उसी ऑर्डर में ट्रैवर्स कर रहा हूँ, तो ये दिस इज डेफिनेटली ऑर्डर 1। इवन इसके लिए भी अगर हम सोचें तो ये क्या करेगा, इससे लेगा और इससे लेगा, सो दिस ऑलवेज ऑर्डर 1। ओके, सो आई थिंक देर इज ओके, वो 15 वाले को फिल करने के लिए 1 and 8 तक ट्रैवर्स करना होगा ना। ओके, मैं समझ गया कि ट्रैवर्स करने से आप क्या मीन कर रहे हैं। सो 2D सेगमेंट्री हम लोग 2D तरीके से ही इंडेक्स करेंगे। हम बोलेंगे नॉट ओनली ट्री ऑफ आई, हम बोलेंगे ट्री आई जे, ठीक है। तो अगर हमें 15 के लिए इधर जाना पड़े तो इट विल बी जस्ट लाइक इंडेक्सेस। हम बोलेंगे 2i में चले जाओ, 3i में चले जाओ, 2i और 3i, सॉरी 2i प्लस 1, 2i और 2i प्लस 1, ऐसे हम डायरेक्टली पहुंच जाएंगे। ऐसे नहीं कि उस सेगमेंट्री के रूट पे पहुंचेंगे और वहां से जाएंगे, these are all like arrays to us. So arrays में हम खेल सकते हैं. अब हमें पता है कि किस order में हम, basically the order is dictated by the tree and the rest of the things are taken care by the array. Maybe if we get some time in the next sessions we can discuss on it. क्योंकि heaps में उतने time नहीं जाएंगे. heap sort है इसके बाद शायद, तो उसमें उतने time पे नहीं लगेगा. We can actually fetch these topics and we can discuss this in greater detail. अभी I think आपके वो snack down related कुछ series है, advanced topics का कुछ series चल रहा है, so you can maybe attend that. I won't extend this class from here. Next दिन वापस continue करेंगे. I think, like, I'm not sure about the schedule. So I hope you have got some idea. So 2i and 2i plus 1 यूज करने से ऑटोमेटिक वो चाइल्ड सेगमेंट्री के एग्जैक्ट नोड पे एग्जैक्टली ऐसा नहीं कि ये ब्लू वाले से पहले जाना है फिर जाके, ऐसा कुछ नहीं. ये जो ग्रीन आपको दिख रहा है, मतलब ये सारे इंडेक्स्ड है, तो आपको पता है कि इससे कैसे इधर तक जाना है. ओके ये मैंने x इक्वल टू 4 दिखा है. सिमिलरली आपको y वैल्यूज है, y इक्वल्स टू 4 ऐसा कुछ है. सॉरी y इक्वल्स टू 1 होगा इधर, y इक्वल्स टू 2 3 4 5 6 7 ऐसा कुछ है. ठीक है, great. Then any questions before we finish? I'll wait half a minute and then we'll conclude. Hope you learned something out of this course so far as we have done till now. Hope you have got something that you can apply, or some ideas that maybe you can apply, and some problems which you can directly compare with some other problems and solve them. Okay, my pleasure. Okay then, I hope it is the same with all. Have a nice evening. So yeah, keep coding. Take care. Bye.